Welcome back, everyone. We are in our second to last session. This is the Exoplanets Astrobiology room. As a reminder, we'll have time for questions. When you ask a question, you should say your name. I'm Courtney Dressing, and your institution. I'm at UC Berkeley. I use she, her pronouns. And if you have questions and you're in the room, you can either raise your hand or you can put them in Slack. If you're online, please put them on Slack, not in the WebEx link. Our first speaker is Professor Andrew Vanderberg from Harvard Center for Astrophysics.
All right. Thanks so much for all being here and sticking around till the last afternoon of the conference. I'm really excited today to talk to you about an opportunity to learn what rocky planets are made of and how that will help the HWO and how the HWO can help that endeavor. This is work that's been led and really spearheaded by these two people. One of them is Mariona Bedene-Segusti. She was a grad student in my group and recently graduated to become a postdoc at Cambridge University. And Javier Viana, who is at this conference and who is a machine learning expert, and you should absolutely chat with him if you have a chance. So one of our major goals, as we've heard all week, is that we want to find these potentially habitable exoplanets. And our best ways for finding exoplanets these days tell us about things like size of a planet, its temperature, its mass, and even some things about its atmosphere. And these are things that are what we're able to most easily measure. I won't say it's easy because it's been a long way to get there and it's really impressive what we're able to do. But there's another thing that's really important that we have a harder time understanding, which is what are the interiors of these planets made of? What elements and minerals make up the rocky planets in our solar neighborhood? And this is important for a variety of reasons. I'll give you just a couple of examples of why this is something we should care about. So for one thing, the longevity of plate tectonics is a major factor in terms of habitability. It tells us how long we'll have a magnetic field. It controls various geological cycles. And this lifetime is largely determined by the heat conductivity of the interior, which depends on the mineral content. And one of the variables that controls what minerals we predominantly form is the magnesium to silicon ratio. So if you have more magnesium versus silicon, you can form either pyroxene or olivine in different proportions, which affects longevity of plate tectonics. Another reason why we should care about this from the HWO perspective is that we have to worry about when we detect oxygen with HWO around a planet outside the solar system. Could it have been formed by life, or could it have been formed by some other abiotic geological process like outgassing? If you want to know what species are going to outgas from a planet, you have to know what those planets are made of and what the elemental composition is. You want to learn about something called the oxygen fugacity, which is, for example, how many free oxygen atoms there are around, and therefore that will tell you whether you're more likely to outgas a lot of O2 and O3. So there's lots of good reasons why we should understand generally what the range of compositions of rocky planets in our solar neighborhood is. But it's hard to actually make these measurements. So if we wanted to figure out what a rock is made of here on Earth, what we would do is we would take the rock, we would crush it up with a hammer, and then we would take it to our lab and put it into a spectrometer. Unfortunately, it's a little bit harder and maybe more morally questionable to do this to an exoplanet. So instead, we'll let the white dwarfs do the dirty work for us. White dwarfs are the burnt-out cores of stars, like our sun, that are left over after the star runs out of nuclear fuel. They're very dense. They typically have half the mass of the sun, but they're about the same size as Earth. So they're 300,000 times more massive than the Earth. And as a result of this, white dwarfs have extreme gravity on their surfaces, and they're chemically stratified. At the top of the white dwarf, you have the lightweight elements, hydrogen and helium. And everything else that's heavy should sink to the center of the white dwarf on fast timescales. And in fact, this is what we see. When we look at the spectra of most white dwarfs, we see blank slates with only spectral lines from hydrogen and sometimes helium. But in other cases, something else is going on. And what's going on is most likely that leftover material from the planetary systems that survived the post-main sequence evolution of the star from a main sequence star like the sun into a red giant and then losing its outer layers to become a white dwarf. These planets and asteroids and comets may have survived, but they may have been subjected to new gravitational instabilities due to the mass loss on the red giant branch. So even if you might have had some sort of stably orbiting Ceres-like object like I'm showing here, after a while, there might be a dynamical instability that sends that object a little bit too close to the white dwarf, where it gets close within the tidal radius, is ripped apart by the extreme gravitational forces of the white dwarf star, crushes itself up through collisions into a disk, and then material from that disk streams onto the white dwarf. And now you have the remnants of planets in gaseous form vaporized on the surfaces of the white dwarf, and we see that in the spectrum of these stars. So what we've effectively done here is use the white dwarf as a mass spectrometer. We can now see what the elements were that made up these planets after we crushed it up in this debris disk and had it stream onto our light source. This is our best probe of extrasolar geology today. Unfortunately, we haven't been able to fully capitalize on this approach. And one of the reasons is because it's really time-consuming and difficult to make measurements of the abundances of white dwarfs. If you want to do this, you need to model the spectra really well. And typically, this isn't a time-consuming process. It takes a long time to generate and have good convergence in white dwarf evolutionary and stellar models, or structure and stellar models. So the models that we use are from a group in Montreal, and it typically takes 1 to 3 hours to generate one of these models. And if you want to then take those models and tweak them until you have a good fit to all of the abundances, it's a long, time-consuming process that involves a lot of by-hand tweaking. And as a result of this difficulty, the number of white dwarfs with lots of elements where you can measure their abundances and therefore measure the ratios and learn about what the composition of the planets are is relatively small. Only about 30 white dwarfs have measurements of more than about 5 elements in their spectra. So to address this, Mariona, for her PhD, developed Cecilia. What Cecilia is it's a way to speed up the generation of model spectra. It uses a neural network to interpolate spectra and effectively use a more sophisticated version of grid interpolation to emulate the spectra from these models and give a really, really fast computation of what the white dwarf spectra should be given input parameters like temperature, surface gravity, and elemental abundances. This is inspired and very similar to work by Jensen Ting, who develops a code called the pane. As a homage to Cecilia Payne-Gaposchkin, after which the pane was named, we called our code Cecilia. So the heart of Cecilia is this neural network that takes the input parameters and spits out a spectrum that closely mimics these models. We've played around with several architectures. This is the one that ended up working first well enough to make some progress, so that's what we went with for Mariona's PhD thesis. Probably we can improve upon this, and that's an active area of our ongoing research. But what we were able to do once we had this neural network was to dramatically speed up our model calculations by orders of magnitude. It took us about 3 weeks to train the neural networks on a supercomputer end to end. But after we did that, we were able to generate a model spectrum in only 10 to 100 milliseconds. So we can dramatically speed up this process, and that's fast enough that we can actually use modern statistical methods to model these spectra. Now we can do things like run MCMC with our model spectra and measure the parameters of all of these different elemental abundances simultaneously and learn about covariances between these parameters. This is an example fit to Sloan Digital Sky Survey data. And you can see here that our model works really nicely. It fits all of the spectral lines, and it seems to give consistent answers with literature. We're now trying to take the success from that one spectrum and include and apply it to more spectra that we didn't actually know the answer to before. So Mariana has recently had a paper accepted in Monthly Notices where she does this for 5 new white dwarfs and measures the abundances there. So this is a possible way that we could scale up our ability to learn about extrasolar geochemistry. Here's a case study from one of these spectra, from one of these white dwarfs. We can take the elemental abundances, convert them to what we think must have fallen onto the white dwarf in order to produce this kind of contamination in the spectrum, and compare this pie chart here, where yellow is oxygen, pink is iron, and the other elements are listed like this, to what we know the compositions are of solar system bodies. And in this case, we can see that this object pretty closely matches chondrites, or primitive meteorites in our solar system. The magnesium to silicon ratio is pretty similar to what we have in our own solar system, so it looks like we have a similar level of olivine production, which means that on this system, if there were an Earth-like planet, potentially plate tectonics would be similar to what they are here on Earth. But only applying it to a handful of examples is kind of limiting the power. What's really exciting now is that there's these huge spectroscopic surveys that are looking at hundreds of thousands of white dwarf stars. And if we can take the data from all of these and apply this rapid automated procedure to them, we'll be able to get population level constraints on elemental abundances. And what that means is that once we discover a planet with the HWO and we see oxygen, we can calculate how weird would the elemental abundances need to be on this planet to outgas this much oxygen. And then we can compare that to our distributions that we measure from the white dwarfs. And if they're consistent, then maybe this is a relatively weak detection. But if you need way more oxygen, free oxygen to be able to do that, then maybe this is a case where we have a really strong biosignature. HWO is also going to be excellent for this because many of our best constraints on volatile elements and around white dwarfs need to come from the ultraviolet. HWO is going to have the most powerful ultraviolet spectrometer ever. We're going to have a 6-meter aperture with modern detectors and really good quantum efficiency. And having the ability to go into the ultraviolet where many of the volatile elements show the most lines will be really powerful and let us do this science even better than we can right now with current resources. So with that, I'll put my conclusions up before Courtney comes and tells me I'm out of time, and I'll happily take questions. Thank you.
What questions do you all have? See a question in the back? I'm going to start here, and then we'll send the mic up to the back as well.
Great talk, Andrew. So if we want to go from the abundance measurement in the contaminated white dwarf to the composition of the rocky planets, what additional model work do you think that are essential and necessary?
Right. So there's one basic conversion, which is you need to make an assumption about the accretion rate. Is the accretion kind of in a steady state, or is it being dumped on episodically, or is the accretion over, and is it all just kind of sinking down to the core? Usually it's a pretty good assumption to know that it's in the steady state because we know that white dwarfs often are polluted. There's a large fraction of them that are polluted, and it seems that if that is the case, then they should be all slowly accreting because we think that these disruption events should be relatively rare. So it means that each one of them should take a little bit of time. So most of the time we're going to be looking at them in steady state. We may be able to break that degeneracy and see cases where there is like a really episodic dumping happening looking at X-rays, which can tell us about the accretion rate overall in a different way. And we can compare the accretion rate that we get from the X-rays to what we would have expected if this were in steady state and see that it's different. And then there's other model problems as well. I won't say problems, but challenges. It turns out that we don't really understand the physics of hydrogen at these extreme pressures and temperatures perfectly, which means that all of the equations of state that go into these could be wrong, and that could change our measured abundances and ratios at the level that becomes interesting. So there's a lot of work that we could do with maybe experiments trying to use Z-machine type devices to measure the equation of state of hydrogen at like super high temperatures and pressures that would help out there.
Hello. Hello, Rodrigo Ferrer Chavez from Northwestern. Could you say a bit more about the training process? What data did you train on? Can it be used? Can this Cecilia code be used in any astrophysical object spectrum?
Yeah, so we trained on synthetic data. We took a library of synthetic spectra and we knew the input values to produce those synthetic spectra, and then we asked it to produce those. So we could generate as much data as we wanted, and it was effectively perfect because we're assuming that we just want to replicate the models. There's, of course, the problem of we then inherit the biases from the models, but that's kind of what we were doing anyway before, so it works pretty well. I think we had like 20,000 spectra, but we're upping that for our next round to something like 100,000. It's mostly limited by the computation we need to generate that training set.
Great, thank you, Andrew. Let's give Andrew another round of applause. If you have more questions, put them on Slack and tag Andrew. Our next speaker is Anna Grace Olses from the University of Washington.
Hey, can everybody hear me all right? Okay, so yeah, I'm Anna Grace. I'm entering the third year of my program at the University of Washington. Since I submitted my original abstract, I've expanded this talk to include a little bit more about what we've been generally trying to do to characterize terrestrial exoplanet surfaces using reflected light spectroscopy. So the reason we care about surfaces in general is because they can help us provide the necessary planetary context that will enable us to accurately interpret future biosignature observations. Now, generally speaking, a biosignature is any detectable feature of a planet that we can use as evidence of life. More specifically, I'm going to differentiate between atmospheric signatures, such as molecular oxygen or methane, as well as surface biosignatures, Some of you may know the vegetation red edge, and we're also considering the presence of large microbial communities as a potential surface biosignature. So in the pursuit of providing broader planetary context for biosignatures, I'm going to be discussing how we can characterize 4 broad categories of surfaces. First are oceans, which is a very strong habitability indicator, and then continents, which we consider an oxygen biosignature false positive discriminant. And then we're going to be talking a little bit about surface biosignatures. Okay, so the driving scientific question behind why we're actually interested in looking for land, other than the fact that it's kind of interesting, we can use it as a tool for discriminating between abiotic oxygen and true biological oxygen. So in other words, we're trying to be as confident as possible that any oxygen we observe in the atmosphere of a terrestrial exoplanet actually has a biologic origin and doesn't come from some broader planetary process. So we heard yesterday about some of the known pathways for generating abiotic oxygen in the atmospheres of Earth-like planets around sun-like stars, and the scenario I'm going to be focusing on today is a planet that initially has a very large water inventory exceeding about 50 Earth oceans. The pressure at the base of that ocean increases the solidus, or the melting point, of the underlying silicate mantle, and then gradually, over a few billion years, fresh crustal production will cease, and then geological oxygen sinks like the outgassing of reduced species or water rock reactions are going to be suppressed. What that means is that through the normal processes of water photolysis in the upper atmosphere and then subsequent hydrogen escape, oxygen will build up in the atmosphere. So we call this scenario a water world biosignature false positive. Fortunately, we can observationally rule out a water world planet by constraining the ocean depth with land detection. This is because exposed land precludes extremely deep oceans, given topographic limits set by the crushing strength of silicate rock. So going about this in practice requires compiling the reflection spectra of various plausible surfaces that we're likely to expect to find on terrestrial exoplanets, which is what I'm showing here on the left. The main idea that I'm trying to convey with this figure is that the land surfaces we compiled, and as far as we can tell, they all slope positively in the visible to near infrared region of the spectrum, whereas the ice surfaces are very negative in the same region, and ocean is very flat with a low albedo. What we then do is we parameterize the planetary surface as a weighted function of these individual land, ocean, ice surfaces, which is what the dotted black line on this figure is showing. Then we can put that surface under an Earth-like atmosphere and compare it to what a water world looks like. So that's a planet with just 100% ocean. Here on the right, the green line is our lifeless Earth-like planet with 30% land coverage. And if you directly compare that to the blue line here, which is the water world, there's 2 obvious differences between these spectra. The first is when you include land in the surface, the overall albedo of the spectrum is increased. But more importantly, and also more diagnostic of land, is that we find that red slope in the visible to near infrared. So after that forward modeling process, we can run retrievals using RFAST, where we're simultaneously retrieving atmospheric abundances, parameters describing what the surface is composed of, planet mass and radius, and then the properties of our gray cloud model. So what I'm showing in the top right is an example of one of those retrievals where the red line, or the red spectrum with the confidence interval, is our true lifeless Earth, and then the blue spectrum is what our retrieval found. These spectra match up really well, but in order to really interrogate what the surface looks like, we can extract just the surface, so we're taking away the atmosphere here entirely. And the thing that really pops out, at least in my opinion, is that you're really picking up that slope in the visible to near infrared that you expect to be attributable to the presence of land. So this figure here is showing 3 different retrieved surfaces for different wavelength ranges, and I'm comparing them to that lifeless Earth spectrum that I showed before. As I said before, yeah, you're finding that slope that we were looking for to begin with. We can go even further in the analysis and extract the total land fraction posteriors for these kinds of retrievals. I'm showing here 3 different cases for increasing SNR of 10, 20, and 40. What we find is that across a wavelength range of 0.2 to 1.8 microns, in order to constrain an Earth-like land fraction, so here we're saying 30%, you'll need a minimum SNR of 20, which is the green distribution I'm showing on the slide. So next we decided to test what kind of wavelength coverage you minimally need to achieve this detection. The main, or arguably the most important result from this analysis is that you need a little bit of ultraviolet spectroscopy down to at least 0.3 microns, which is the dark blue posterior I'm showing here. If you exclude the ultraviolet entirely, it results in a non-detection, which is the dark red contour here. The main reason is because when you exclude the ultraviolet, you're not independently constraining ozone, and that leads to degeneracies in the retrieval that it's not able to break. So then we looked at the long wavelength end of things, and we found that at an SNR of 20, going beyond 1.1 microns doesn't really lend much to land detection. But as we heard yesterday, and we've been hearing a lot throughout this conference, there's other science cases that push the wavelength range farther into the near infrared. Okay, so the main caveat to the analysis I've been showing before is that we were assuming some sort of knowledge about what the surface is composed of, as well as what sort of fractional coverages we might expect. Now, in reality, those are potentially some of the greatest unknowns. So in order to get around that issue and generalize the process a little bit more, instead of parameterizing the surface as a weighted function of different materials we find on Earth, we can instead use polynomial functions, which I'm showing here on the right. So what we find is that using this agnostic parameterization, for all of our chosen polynomials, the retrieved surface spectra are inconsistent with oceans for all parameterizations, and indeed they demonstrate that the surface requires some sort of positive slope behavior, meaning that we've been able to infer the presence of land without having to know what it's actually composed of. Okay, now to round out this analysis, we're also interested in how many actual observation hours you need to make this kind of observation. So in order to reach the minimum SNR of 20 for detection, we found that integration times across the wavelength range of 0.3 to 1.1 microns hover around 200 hours for an 8-meter telescope. When you decrease the diameter of the telescope to 6 meter, those observation time hours increase by a factor of around 2.5. So naturally, we favor a larger aperture in order to make these observations in a reasonable amount of time. Okay, so another big question for HAB worlds, and a question I have myself, is how can we use it to first identify a habitable planet, let alone a planet that may actually have life? So in the direct land retrievals I was showing before, we were retrieving the ocean fraction implicitly as 1 minus the sum of all other surfaces, which means that we're able to plot similar total ocean fraction posteriors, which I'm showing here on the left, for, again, a selection of wavelength ranges. The short of using this method to try and find oceans is that it will likely require a higher SNR of 40. And even though our posteriors peak near the true value of 60%, they have long tails towards 0, which leaves it open to some ambiguity. Then similarly, we performed agnostic retrievals of water world surfaces, which I'm showing here on the right. And our retrieved surfaces are suggestive of a flat surface albedo, but confidently attributing this to oceans will likely require further work. Okay, so finally, after building up this method for detecting land and oceans, we thought, okay, why don't we actually probe actual surface biosignatures using this method? So there's a lot of lines up here, but what I want to communicate with the figure on the left is that not only are potential surface biosignature very diverse, they also have very unique edge-like characteristics due to their biological structure and the pigments they contain. One of the most well-known of these features is the vegetation red edge, which I'm showing in the green line here, which is associated with a very sharp increase in albedo around 0.7 microns. So similarly, when we map a surface biosignature to its most likely era of Earth, we can create a picture of how an inhabited Earth might look like through its different eras in reflected light. So that's what I'm showing here on the right. I should say as well that in our retrievals, we were prescribing a surface fraction of 15% for all of the biological surfaces. So here I'm showing two of our most optimistic cases from this analysis. On the left is the modern Earth. Now again, we're just looking at the surface, so there's no atmosphere here. But our retrieved surfaces, for 3 different SNRs, they pick up the vegetation red edge very well, around 0.7 microns, which is exactly where you expect it to be. And also, we're finding the more gentle slope of land in the visible. Now, taking a look at the posteriors for what the retrieval thinks the surface is composed of, we find that constraining a pre-anthropogenic forest fraction of about 15% requires an SNR above 20. And now looking back in time at the early Archean, similarly in the visible we can find the evidence for biological pigments, and we're finding the slope of land. And the posteriors tell a similar story where you're going to likely need a SNR above 20 in order to make these detections with HAB worlds. Now the chart I'm going to show next is a little bit busy, and we saw a version of it yesterday. All of that just to say that this is ongoing work, so we're currently working to expand and fill out the parameter space in order to really refine the minimum requirements for HAB worlds in order to make these detections. And I'm probably going to just go to the end of my conclusions here. I'd like to acknowledge funding sources as well as collaboration with the Living Worlds Surface Biosignature Task Group. And I can take any questions. Thank you.
What questions do you have? All right, Renya.
Great work. I wonder, what do you assume as clouds in these retrievals?
As what, sorry?
What do you assume for clouds in these retrievals?
Oh,
and
yeah.
what do you assume as the knowledge for clouds in setting up the retrievals?
So for all the retrievals I showed specifically, we had a 15% fractional cloud coverage, so that's over the entire planet. And then the bottom right of the retrieval here are the different parameters of how clouds are parameterized just in this version of RFAST. There's 4 parameters in total. I know there's opacity, total fraction, cloud top pressure, and there's one more that I'm forgetting. But those are also retrieved as free parameters.
Any other questions, either online or in the room? Yes, and if our next speaker could go ahead and come up and get you mic'd up.
I noticed that the ice and the ice and the snow didn't have this slope. Was that true? And did you think about if you were? I took an astrobiology class 7 years ago, so I might be wrong. But there's snowball Earth times when would it all be ice at that time, or is there still a slope?
If the planet's covered completely in ice, yeah, you probably wouldn't find that slope in the visible to near infrared. Would be my guess. I think you'd find an equivalent downward slope a little bit farther into the near infrared, but you'd be able to tell those apart. It's just my guess based on this work. So.
All right, we have time for one more question. See a hand. I love all these questions. Thank you so much. Remember to say your name and your affiliation.
Hello, Noah Tusho, NASA Goddard. I had a question, which maybe it's me being ignorant of the topic, but how can you differentiate between atmospheric biosignatures and surface biosignatures? Because I know that we're talking about identifying I guess maybe biosignatures is the wrong term here, but just trying to distinguish between the land fraction or the chemical composition of the atmosphere. So I was wondering if we didn't know anything about the atmospheric composition, if we weren't assuming an Earth-like atmospheric composition, could we actually accurately constrain the land fraction as well?
Yeah, so in the retrievals, we're also assuming all of the atmospheric abundances are free parameters. So you don't need to know what the atmosphere is composed of either in order to constrain land.
Okay, so the atmosphere varies freely and also the...
Yeah.
Okay, thank you.
Great, let's give Anna Grace another round of applause. And I believe I saw a link to a paper, so look for that.
Yes, thank you.
Our next speaker is Tara Matsuo from Osaka University.
Yes, thank you very much for giving us this opportunity to present our latest study on the possible biosignature for HWO. The starting point of my talk is this image. It doesn't work. So taken by Boja-Wan in 1990. And so this image inspired Dr. Carl Sagan, and he left the very famous phrase, pale blue dot. So since then, the pale blue has become it's kind of a symbol for the cradle of life in the universe. So of course, the Earth, so the blue comes from the atmosphere and also ocean. But my question is, so was the Earth always blue? So through the history of the Earth. So the reason why I raised this question is the surface environment has been gradually oxidized through the oxygenic photosynthesis. So there might exist various chemical compounds generated through so redox reaction under the oceans, and leading to the different color from the blue. So one good example for this is the blue tide. So this picture was taken in the Tokyo Bay, and the specific, this color comes from the scattering effect of colloidal sulfide, so which is also generated through the redox reaction, so induced by the human activities. So now we go to the Archean and Proterozoic eras. So of course, one of the important geological records is the global oxidation event called GOE. So there are two especially meanings from different perspectives. So one is the evolution of life. So of course, the surface environment could promote the birth of the aerobic respiration, so such as eukaryote. And another is the astrobiology, so search for life. So this global scale surface change, it could be detectable, and also even though this planet cannot be spatially resolved. But we have not fully understood the origin of the first oxygenic photosynthesis, so cyanobacteria. So now one of the, so we focus on the cyanobacteria, so for now. So one of the interesting features of the cyanobacteria is the light harvesting antenna called phycobilisomes. So phycobilisome apply the very special pigments like called phycobilin, so to absorb the green and so red light. So that complement the chlorophyll A, so regarding the absorption spectrum. But however, in order to transfer the light energy from the antenna to the reaction center of the chlorophyll A, so now the phycobilisomes become more massive and more complex compared to the general light harvesting antenna such as LHC for the green algae and land plants, so which is composed of the chlorophyll A. So now we narrow the general question of cyanobacteria into this. So why did cyanobacteria apply the very special pigments to absorb the green and orange light, so rather than the universal pigment of chlorophyll A? So one of the interesting facts, so we focus is so when they emerged. So for example, cyanobacteria emerged in the Archean era before the global oxidation event, so which means they were developed under the fully reduced environment. In contrast, the other oxygenic photosynthesis, phototrophs, emerged under the partially oxidized or fully oxidized environment. So now, during this kind of oxidation process, so the light environment could also shifted gradually. So now we focus on the underwater light environment, so for their habitats. So before the birth of cyanobacteria, so the atmosphere and also water environment were fully reduced, so indicating that the reduced iron could be fully dissolved in the water and spread over the entire sea. But once the cyanobacteria emerged under the water, so now the surface water started to be gradually oxidized. And this iron oxide was also turned into the iron hydroxide, so as a particle. And based on our measurement of absorption coefficient of iron hydroxide, as shown in the right panel, so now we've noticed that the underwater transmission spectrum is constrained to green rather than the blue. So, and in order to test this theory, so we performed a field experiment around Io Island in Kyushu, because so Japan is surrounded by the volcanic activities, and then So around this island, so there are many hydrothermal vents, and they are supplied. They supply the reduced iron, and then they are quickly oxidized to iron oxide. Then we conducted the measurement of underwater transmission spectrum at the depth of the 5.5 meter, and so we confirmed that so clearly green light environment was formed. And also, based on the measurement of the absorption spectrum, so we could reproduce this kind of spectrum so in our simulation. So now, based on these data, and also including the biological experiment on the phylogenetic analysis, so I do not talk today, but so we draw the coherent scenario connecting the evolution of cyanobacteria to the transition of light environment. So, but my main message here is so that cyanobacteria have developed under the green light environment around the great oxidation event. So now we expand this theory to the astrobiology, search for life. So the underwater light environment is also connected to the albedo of the oceans. So because the iron hydroxide efficiently scattered, scattered light so under the water. So in fact, the remote sensing data shows that the 10 times higher albedo in the green oceans compared to the typical blue oceans. And also, so we can see so there is a distinct spectral edge around 550 nanometers thanks to the strong absorption of the blue light by the iron hydroxide. So now we discuss the scientific value of green ocean scenario. So first of all, green ocean formation overlaps with the period of the banded iron formations. And so spanning from the 3.5 gigayear ago to the 1.8 gigayear ago. So, and this scenario could tell us about the first oxidized surface environment through the history of the Earth. But of course, we need to understand the abiotic process, UV oxidation. So now we have modeled modeled two scenarios with cyanobacteria and without cyanobacteria. So, and I do not go to the detail, but compared to results, we now realize that the abiotic process is 100 times less efficient than the biotic process. So because the UV radiation can be efficiently absorbed by the iron hydroxide, also based on the previous study, so quantum yield of UV oxidation is much lower than the abiotic process. So now finally we reproduce the albedo of the two scenarios. So one is a biotic process and another is a abiotic process. And so as you can clearly see, so abiotic process cannot change the color of the ocean into the green. So now I want to say green oceans could be the good tracer for the oxidized environment. Even before the great oxidation event. But of course, we should not forget the photoferrotrophs. So at this time, so the green oceans may be a good tracer for the existence of phototrophs on the distant planet. Thank you very much.
Let's see. I see a question in the front. Nikki has a question.
Okay, so, no, that's okay. So we took the biotic process spectrum there and sort of just superimposed it on the ocean. So outside of that feature, the spectrum we assume is just very flat. And then I ran retrievals similar to the ones I showed about the surface biosignatures and found it to be one of the most potentially observable scenarios along with the vegetation red edge. So it's a very promising biosignature.
Thank you very much.
Great. Any other questions? I'm going to ask one. Can you tell us more about the field work you did? How did you collect your observations?
Oh, thank you very much. So we conducted a field experiment to measure the underwater transmission spectrum. As shown here. And also, we also measured the abundance of the cyanobacteria under the water. So, and we also the composition of the water. And so now we had a coherent scenario. So because, as you can see, that this underwater transmission spectrum can be reproduced by the iron hydroxide of the 10 micromolar concentration. And this value is also matched with our measurement of the iron hydro concentration.
Great, thanks. Okay, let's thank our speaker one more time.
Thank you very much.
Thank you.
All right, our next speaker is Marco Landoni, who will tell us about AI-assisted observational strategies for HWO.
Thank you. Thank you. It's a pleasure to be here. So I try to give you an overview of what we are currently doing at my home institution in Italy, in February Observatory. We're doing something from ground-based, actually, but it could be somewhat applied next, maybe in the space. So just to give you an outline, so I'll try to be short, giving a goal for automated scheduling, so something that we can try to implement also for HWO. An historical overview is something absolutely not new, we already know, but it's gaining more and more popularity right now for managing telescopes remotely, for example, especially we're trying to do something for ESO, I'll show in a while. With a Bayesian approach and the machine learning approach. I try to adapt a bit the presentation since most of the science cases and topics that we discussing in these days are most related to exoplanets, actually. And why it's so important to start at least to think about right now. So which is the goal of automatic scheduling? It's something, trivial, but important to recall. We need to full automation of the scheduled processing. This is for the ground, but I think also for the space. Provide the scheduling for observable targets, and especially it's important to go involved also with the scientific goals we need to achieve with the observation, optimization of the observation quality, and the time that we gain at the telescope to do reliable automated decision, maybe for unforeseen event. This is especially true also for the ground, and for operational tracking. And flexibility, of course, it's a plus that every time is of course needed. This is not completely new. This is, for example, the spike planning and scheduling software, which is, I think, deeply used in Space Telescope Institute from phase 1 to planning and pre-scheduling up to the scheduling in the final observation. But lots have changed from then because we have. I show in a while the possibility to use Bayesian approaches in which we combine both the observation and the data that we are gathering from the observation to define what to observe next and when. I'll show an example. And machine learning approaches. And also with the experience that we're gaining also for the fully robotic telescopes from the ground, in which we also have some more restriction, for example, for the seeing, for the visibility, the weather, and so on and so forth. It's more popular now because we have also the computational power, because most of the algorithms that have been applied before are actually requiring a lot of computational power to be applied. So we have GPUs now, we have FPGA, we have supercomputing, HPC, so this is, let's say, a golden era for applying some kind of algorithms that were prevented before due to this kind of reason. This is just an example, okay? We're not talking about radial velocity, but this is just an example of how we can gather information from the data, from observation to schedule the next one. This is a paper from Loredo et al., Bart et al. That applied for TESS, for example, and people from INAF, in which we try to, let's say, optimize the observation for the follow-up with espresso from the ground plus the target of interest from TESS. And the idea basically is to use a Bayesian radial velocity-based approach in which we do a design of the next observation in terms of time, in this case, using an inference, using the interim results between the next observation and the previous one, okay? Because we have a lot of information, not only the scientific one, but also when to observe the next point, for example, in a radial velocity time series, to optimize the time and get the data when it's actually needed. So the idea is always to optimize a sort of expected utility, like the yield that we discussed a couple of days ago, in which we combine both the utility function, in which we, let's say, we have a proxy of the number of bits of number of information that we could gain from a certain configuration of the experiment, plus the posterior probability get from the Monte Carlo Markov chain of our model. This could be applied in principle to all, let's say, scientific cases in which we can do a modeling based on a Bayesian framework, like Monte Carlo Markov chain and the estimation of the posterior probability. And of course, this is trivial. We try to optimize the E, which is the experiment, okay? So the configuration of the experiment. For example, let's suppose that this is a time series of radial velocity, meter per second, okay? We have some points. And then we do, at the first cycle, a blind Monte Carlo Markov chain to get the parameters of the detected planets, okay? So we could use, in principle, the posterior probability to estimate the utility and then to detect when to observe the next observation by measuring all the models plus the information gain, which is proportional, let's say, to the posterior probability. So in this case, we do an observation for the next point where the information gain is maximized. And in this case, you reduce by only few points the scatter of the data by a factor of 2, roughly. Then you redo it again. So you measure again the information gain. You perform observation in the best point in the series of time where the information gain is maximized. And then you redo again your Monte Carlo Markov chain. In this case, by adding only a few points, in this case we went from 20-something to 27 points, you could reduce by an order of magnitude the scatter of the parameters in your Monte Carlo Markov chain. And actually, if you add the previous point, you could, in principle, increase again the scatter because they were not in the right place in time when to do the observation for the next radial velocity point. The next idea we are trying to test, I have not much result because we're trying to implement it up to now, is to use deep learning AI. So in other words, using what we call reinforcement learning, which is used, for example, for training robots, for example, by having some reward function in which you tell the agent when to do something, okay, and what kind of reward in terms of gain you have. So they are, for example, used in AI or in robotics, for example, and they seems to be very promising for optimize such kind of experiment and observation. So basically moving from supervised learning to this kind of thing like the reinforcement learning, because we have a lot of data from previous missions and previous ground observations to try to train this kind of model. And they're really ideal for a cadence survey, okay? They were, for example, explored also for LSST scheduling, which is more somewhat, let's say, complex due to also the constraint for the observation from the ground. We talk about, this is my last couple of slides, about transient that could be supernova and whatever, that could be also of interest for HWO. And this kind of approaches has been used from the ground at ESO for the New Technology Telescope. We have a spectrograph which goes from 350 nanometers to a couple of microns, which is called SOX, which stands for Sonovic Shooter, which is a larger spectrograph on the VLT. And with our approach, will be the first ESO instrument fully operated remotely from Europe in Chile. And it is based on this framework plus AstroPy plus AstroPlan, which is a package in Python to do this kind of thing. In this case, we basically have two end-to-end actors in this case, in which we have the telescope in Chile and the science team in Europe, and then we start from a schedule, and the schedule is automatically adapted accordingly to the status of the telescope, of the weather, of the seeing condition, and scientific priority directly in Chile using the interfaces from ESO offered at NTT. That's my point, why it's so important now as a seed, when we are starting to think about a new mission, for example. Design the telescope and an instrument, maybe with a quantitative way to test in advance the scientific return. We already discussed it a lot in the previous days. Plan the design the mission side by side with the operation. It could be a plus. We can start to think about it. Okay, so maybe we, for example, I'm more from the ground experience, and from the ground you start to think about after the instrument has been commissioned. Maybe if you think about a bit before, it could be useful also to better drive the design. And test synergy in advance also with ground-based facilities between HWO and ground-based facility observations from the ground. Thank you.
Right, questions? See a question all the way up in the back there, right above the bar.
Hello, this is
Thanks.
Alex
Hello.
Medorowitz from Space Telescope. In your cost function, how would you balance patience with waiting to get the most valuable next data point with the urgency of needing to get the data soon and the results published in a reasonable timeline?
That's a very good question. I mean, at the moment, in this kind of theoretical framework is not taken into account. We are taking into account from the ground-based facility that we have now in NTT for SOX, and we are, let's say, try to optimize accordingly to 3 points in this case. We're not doing this kind of thing. Okay, first of all, so we're not based on radio velocity, so we don't have this kind, let's say, of convolution of waiting for the next point and the next point to be observed. But in this case, to cope with all the scientific cases, we do a sort of prioritization between the priorities given by the panel that allocate the time, plus the probability to get a successful observation accordingly to the weather condition that you could have, the seeing, and so on and so forth. If we have to move also to include the physics and wait for the time, I think it will be more difficult, especially for the velocity.
Thank you.
We have an online question.
So this is a question from Akib. Could you please comment on what type of RL model did you use? Did you feel the need to try more than one frameworks?
Sorry, I didn't get the point.
What kind of recursive learning model did you use, and did you try more than one of those models?
In the reinforcement learning. So, I mean, we were just testing a couple of, let's say, out-of-the-box model that are very, the Q model, one is one that we're trying to use. It's very preliminary because the most difficult part here is to get a good data set between observation gathered from human and how to train the model. But the one that we're using is the standard Q learning model for reinforcement learning. This is the one that we're using at the moment. I mean, start to test to try, okay, because it's something new.
Other questions, either in the room or online?
Thank you.
Okay, so I have a question for you. You're not through yet. So my question is, when you think about doing this adaptive learning on HWO, how much of it do you think would occur on the ground using larger facilities here, and how much would occur on the observatory itself, and what would the demands be on onboard computing and power?
So you mean if it is too, let's say, complex in terms of computational power? That's the point?
Yeah, like how much of the decision do you think would be made on the spacecraft with resources there versus how much would be sending spacecraft data and telemetry down to Earth, making decisions with computers here, and then corresponding with HWO?
In my view, it should be done from the ground. So I'm not expecting something into the spacecraft. Although these kind of models, in general, are not very computational demanding, in general. If you train before, you can use it directly on the spacecraft. But in my mind, the best would be to do it on the ground, actually.
Great, thank you.
Thanks a lot.
All right, thanks everyone. All right. Our next speaker is Kaz Gary from the Ohio State University.
Okay, can you guys hear me pretty good? Good? Okay, great. Thank you for saying the. I was gonna get to that. Yeah, so hi everyone, my name is Kaz Gary. I am a third-year PhD student going into my fourth year at the Ohio State University. And today I'll be talking about my research with Drs. Scott Gowdy and Eduardo Bendek on exploring the masses of directly imaged Earth-sized planets using ultra-precision astrometry. So before we get into the actual talk, I'll just go over a quick outline of what we'll be discussing today. So we'll start with some background on astrometry as a viable method for measuring these planet masses. I'll then talk about how we went about quantifying specifically the photon error budget for these signals. And then next, I'll discuss our results based upon the simulations and what we found were the most important factors in designing an astrometry survey with HAB worlds. And then I'll finally end with our next steps in quantifying the full astrometry error budget. So one of the primary goals of HAB worlds is to detect biosignatures in the spectra of directly imaged Earth-sized planets. So in order to correctly interpret the spectra we get, recent studies have shown that the priors on mass and spectral retrievals affect our detection and identification of biosignatures. So in this plot from Domino et al. 2025, the authors simulated the spectra of a modern Earth atmosphere and ran a spectral retrieval with 4 different scenarios. So these are the posterior distributions for the parameters in each of these 4 scenarios, and they married in these different scenarios, they varied the mass priors. So in purple, mass was treated as a free parameter with no priors. In pink, mass was given as a 2D prior based upon physical densities of the planet. And orange and yellow were the posterior distributions of the retrieval when a 30% and 10% Gaussian prior was used. So as you can see, the only scenario in which the dominating molecules N2 and O2 are both accurately retrieved are with a 10% Gaussian prior on mass. So you can see, you can see the N2 here and O2 there. And so this is just one piece of evidence that the precision of mass measurements influences our interpretation of planet spectra. So our project aims to explore how we can measure the mass of these Earth analogs with a reasonable error of about 10% precision to accurately retrieve the dominant gases in these Earth-like atmospheres. So now that we know why masses matter, let's talk about how we're going to get them. So there are 2 methods of measuring an exoplanet's mass, through radial velocity and astrometry. So both measure that so-called gravitational wobble that an exoplanet's gravity exerts upon the star, but with radial velocity, we measure the Doppler shift of the stellar spectral lines, and with astrometry, we measure the physical movement of the wobble on the sky. And so radial velocity has been used to characterize the majority of the planets that we see today, because measuring that Doppler shift of the stellar spectral lines for a given planet mass and period is generally easier than precisely measuring the positional changes of a host star. However, radial velocity is not a viable method for measuring these masses around all stars. So stars hotter than 6200 Kelvin have higher rotational velocities, making their spectral lines more broadened. And so you can kind of see this here on the top panel. We have a star with a large rotational velocity, and thus the lines are broadened. And then on the bottom panel, we have that same star with a smaller rotational velocity, so the lines are thus unbroadened. Additionally, as we go to higher and higher temperatures above the 6200 Kelvin, we have less spectral lines due to dissociation in the stellar photosphere. So radial velocity relies on that precise Doppler shift of spectral lines, and with a smaller number of lines, and those lines being broadened, the tiny signal of the planet is no longer detectable. So this puts a huge constraint on the type of host stars in the solar neighborhood that we'll be able to look for habitable planets. So that leaves us with astrometry. So it's the only method that we have right now of measuring the exoplanet's mass that can be applied to the entire sample of the HAB world's precursor star list, and thus allow us to get a more robust look at the life here in our solar neighborhood. So there are 3 main sources of error that will contribute to that overall astrometric error budget. So on the left, we have the sources of photon error. So that includes, most importantly, the photon noise from the target and reference stars, the aperture, and galactic location, which influences the amount of reference stars that we'll have. In the middle, we have the noise from the detector or the facility. So we'll have noise from detector characterization. And on the right, you have sources of astrophysical noise, such as companions or star spots, that may impact that photometric variability. So my project focuses specifically on quantifying the photon error budget, so to make sure that we have enough photons even in the first place to do this kind of measurement. So according to calculations, the astrometric signal of an exoplanet of an Earth-sized exoplanet is a function of the semi-major axis planetary and stellar mass and the distance from the system. So this can be seen in equation 1, where that astrometric signal, of an Earth-sized planet at 10 parsecs is approximately 0.3 microarcseconds. So in order to get our astrometric signal down to that precision of 0.3 microarcseconds per measurement, we'll need to find the adequate number of reference stars in order to precisely measure that changing position of our wobbling target star. So we can calculate the number of reference stars needed to produce a 0.3 microarcsecond signal by assuming a reference star G magnitude of 18 and an exposure time of 30 minutes. For just one background reference star G magnitude 18 and that exposure time, we measure a 4.8 microarcsecond signal with a 6-meter telescope. So this is shown in equation 2, where that astrometric error on the target star is shown as a function of the reference star's G-band magnitude, exposure time, and the diameter and angular resolution of the telescope. So about 260 of these reference stars will be needed to beat each measurement down to that 0.3 microarcsecond, given the assumption of diffraction-limited Nyquist sampling. So now that we know how many reference stars of what magnitude we'll need to get that one measurement down to the precision we need, we also need to calculate the number of measurements needed for the signal to be detected at an SNR of 10. So this can be seen in equation 3. So if our period of the star's wobble is smaller than the time of each measurement, then our SNR becomes a function of the number of measurements, the astrometric error, and the planetary and stellar mass. So we'll need about 100 measurements of an astrometric signal of 0.3 microarcseconds to achieve that SNR of 10. So just to summarize, if we assume an exposure time of 30 minutes, telescope diameter of 6 meters, a distance of 10 parsecs to the system, we will need 260 reference stars with at least a G magnitude of 18 to measure the astrometric signal of an Earth analog. In order to trust our measurements, we want to get that 0.3 microarcsecond signal with error bars of 0.03 microarcseconds. So this is the precision we are trying to achieve to reliably measure an Earth analog's mass with HAB worlds. It's important to note that no one measurement we take will have this precision, but our goal is to control those systematics in order such that all of our measurements together can achieve this precision. So now that we know the precision that we're aiming for, let's actually find out if we have enough photons to do it. So we use the stellar population code, or stellar population synthesis code, synthpop, to simulate the number of stars per degree per magnitude at different galactic locations. So on the left is the number of stars at the galactic plane, while the right is near the galactic pole, both as a function of the star's magnitudes and the Gaia G-band filter. So as you can see, when we move towards fainter magnitudes, the number of stars in the galactic plane continues to increase, while at the galactic pole, the number of stars starts to plateau. So bottom line, more stars near the plane equals more reference stars in our field of view. So we then assumed a 10 arc minute by 10 arc minute field of view at each location to find the effective number of reference stars. So this is plotted here as a function of filter for different latitudes at longitude 90 degrees. So a black line is drawn at 100 to show the to show the order of magnitude for the number of reference stars we need to get to our precision of 0.3 microarcseconds. So the key takeaway from this plot is that as we get to redder and redder filters, the effective number of reference stars goes up, while vice versa, at bluer filters, the number of effective reference stars goes down. So using the effective number of reference stars from our last slide, we were then able to calculate the astrometric uncertainty in arcseconds as a function of filter for those same galactic locations. So like the last plot, a black line is drawn at the position we need for an Earth-like planet, and we've established that the astrometric uncertainty depends on the number of reference stars, and the number of reference stars depends on both galactic location and filter. But you'll notice, even though we have more reference stars in the redder filters, the astrometric uncertainty, in fact, goes up. So that's because we have a trade-off within the wavelength. The full width half max of our point spread function, assuming diffraction-limited Nyquist sampling, again, for redder wavelengths is bigger and thus less precise, even though you have more reference stars. Vice versa, the full width half max of the PSF at bluer wavelengths is smaller and more precise. However, we have less reference stars. So we found that meeting in the middle, around the V, G, and R bands, balances this trade-off, with the Gaia G band being the most optimal wavelength. So using our simulations, we're also able to estimate the total amount of observational time needed to astrometrically measure the masses of the about 25 Earth-sized planets HAB worlds hopes to study. So this is assuming our only source of photon noise, with the other underlying assumptions up on the slide. So we multiply the number of target stars on the precursor list by the number of observations needed to reach that 10% precision. We also factored in 1 hour of overheads for each observation, and finally multiplied this by the fraction of Earth-like planets in the galaxy, which we assumed was roughly about 0.25. So we came to the conclusion that about 170 days of total time will be needed to astrometrically measure the masses of these planets. So now we can finally fill in that sources of error chart. Great news, we have enough photons to get down to the precision we need. So astrometry is possible with HAB worlds. For our facility noise, we heard from several people yesterday, including my collaborator, Dr. Eduardo Bendek, who estimated the noise from our telescope to be about 0.2 microarcseconds. And from previous studies, we've estimated the astrophysical noise level to be about 0.05 microarcseconds. So noise from our facility will be the dominant source of error in our measurements, and since we're only 1 magnitude away from the precision we need, astrometry with HAB-worlds is worth exploring further. So just to hit those key points again, we estimate about 170 days of observation time is needed to measure the masses of the HAB-worlds planets that we're hoping to study. And now that we've simulated that survey, our next step is to use actual data in order to more accurately calculate the total time needed for that astrometric survey. So we were going to use Gaia observations to determine the number of reference stars in our estimated field of view, tackling this problem with real data. So thank you, and I will take any questions.
Okay, questions?
Hey Kaz, great talk and very cool results. I was wondering if this means that we need to worry about fuel. Because if we're going to be like ping-ponging across the sky to get the right cadence and the right number of observations on all of these stars, which are not going to be in the same part of the sky, does that mean that we're going to spend a lot more time slewing than we would on an observatory like JWST?
Yeah, I think that's a great question. It is honestly one I have not thought of, but I'm assuming that with our, the way that we calculate that observational time, I'm assuming that we would already have picked out those 25 planets. But that is a good point about fuel.
I see another question up in the back. Thanks for running the mic. I appreciate it.
Thanks. This is similar to the previous question, actually. So, yeah, this would be a concern if you need to be ping-ponging around the sky for the slews. And accounting for those slews as well, what is the actual, total cumulative time that needs to be spent, not just the integration time that it would take to get all these observations? So I think the 100 days was accounting for just the on-sky exposures, or does that account for slews and everything in between?
Sorry, just want to make sure.
Okay, overheads are there.
Yeah.
Gotcha.
I think in our calculation when we assumed overheads, we didn't. We assumed a slewing time as well, but I'm not 100% sure what, how much slewing time we assumed.
Yeah, so I'm going to jump in here and point out that this study is really important for doing things like constraining what the slew rate should have to be, and also the settling timescale for the observatory. So I think we're too early to say that we know the slew rate for HWO. That's one of the things that the CSIT will try to place demands or requirements on based on the need to do things like measure the masses of planets. I have a question for you, which is, what do you think the impact of other planets in the systems might be as you're trying to determine the masses of potentially Earth-like planets?
So you're talking about multi-planet systems?
Yes, multi-planet systems.
Yeah, I'm assuming it would be harder to disentangle both of them. I'm not quite sure what the impact would be because when I was doing these calculations, I kind of just assumed they were one single planet system, but we should talk more. That's a good question.
Great. Any other questions, either online or in the room? Okay, this is a reminder, if you have questions for anyone, you can put them on Slack. Just tag their name. Let's give Kaz another round of applause. Our final speaker for this section before we go and have a dessert break and then come back for more talks is Joe Barstow from the Open University in the United Kingdom.
Hi, thank you very much for the opportunity to speak. I'm presenting this on behalf of the Dynamics and Chemistry of Transiting Exoplanets SCDD team, which was led by Hannah Wakefield and Laura Mayorga, with many other people in the audience also heavily involved. So I'm going to convince you that we have not yet done transiting planets with JWST, and there is still so much more that we can do with HAB-worlds. So with JWST, we are probing on the very left of that diagram as you're looking at it. We're looking at transiting planets with periods of a few days at most. With the coronagraph on HAB worlds, we'll be looking all the way out to the right-hand side of that diagram and looking at potentially gas giant planets that are a bit more like Jupiter. But what about the ones in the middle? And I'm not talking about even Earth sort of orbit gas giants. I'm talking about the ones that have orbits of a few tens of days. They are not accessible with the coronagraph. They're inside the inner working angle. So how can we learn about those? Why do we want to learn about those? Well, these are the ones that are sort of approaching around the tidal locking threshold in systems with sort of G, F, K type stars. And the first thing we'd like to know is what's the dynamical regime like on these objects? So for the ones with really short periods, the ones we're very familiar with from JWST, they're tidally locked. They're highly irradiated on one side. They usually have a nice big hot spot. Whereas if you go to the planets that are much more like Jupiter, we know that they have these sort of banded circulations and relatively fast rotation periods. We do not really know what the ones in the middle are going to be doing, and we'd quite like to know. We would also like to understand their chemistry. So for the hot gas giants, we see spectra that are very much dominated by water. We're also seeing signatures of carbon dioxide, carbon monoxide, little bits of methane on some targets, SO2, sodium, all sorts of other things for Jupiters. On the other hand, we've got very much methane-dominated spectra with ammonia, phosphine, acetylene, other interesting cold compounds. Again, what are these planets in the middle going to be like? Are they going to be water-dominated still, or are we going to be seeing more methane on these gas giants? And finally, what are their clouds going to be like? At the very hot end on the left-hand side, we've got things like iron, silicates, some chlorides and sulfides maybe on the slightly cooler hot Jupiters. All the way to the other side, we've got ammonia, ammonium hydrosulfide, methane ice. Do we have water in the middle? Do we have also still chlorides? We really don't know, and we want to find out. Now, we're targeting planets around FGK stars with periods of a few tens of days here. And the way that we would like to do that is by looking at phase curves. So those of you that are familiar with JWST have probably seen these before. A phase curve we obtain by staring at a planet as it rotates around its star, and we see the bright day side going around. We start to see a decrease in the signal coming from the planet as that moves. And then finally, when we see the night side, we've got the minimum amount of signal from the planet, and then it goes back round again. And for JWST, we've done this for quite a few targets now. Here we're looking at the thermal contribution from the planet itself. And it has so far proved to be very informative. This is a phase curve spectrum taken of the hot Jupiter WASP-43b with the MIRI instrument on JWST. So I'm just going to zoom in on the spectra here. So we've got two representative spectra. We've got the day side on the left and the night side on the right. And this was a little bit of a surprise for us because you might, obviously the magnitude of the radiation coming from the day side and the night side is different, but if you look at the shape of the spectra, it's pretty much the same. And that wasn't what we expected, because for this planet, we thought, well, the night side is pretty cold for a hot Jupiter. It's all relative. And so we would expect to see methane starting to be formed at those sort of temperatures. But we did not see any methane at all. In fact, we actually got quite a strict upper limit on the amount of methane that could be there. And that told us something really crucial about the dynamics on this planet. It told us that the winds on this planet are sufficiently fast that a parcel of air that comes around from the day side onto the night side cannot develop methane quickly enough to build up an observable signal before it's whipped back round to the day side again. So phase curves are incredibly informative measurements. And HWO could be an absolutely awesome phase curve machine. So JWST's got a noise floor of about 30 parts per million. Habitable worlds, it should be lower than this. The stability of JWST is not designed to push to really long stairs. So our limit on phase curves with JWST is anything beyond a 2-day period, you're just not going to be able to do it. HWO should be possible to do longer stairs. And of course, the sky coverage. JWST has such stringent thermal constraints. There are quite a lot of bits of the sky it can't look at any given time. We will not have such a problem with habitable worlds. So in terms of targets, thank you very much to Laura for this plot. Here we've got the transiting exoplanet population that we know of now. Those are the circles as a function of host star temperature. That's on the y-axis and period on the x-axis. And that's overlaid by a number of condensation curves from different cloud species. And also, the coloured histogram behind that indicates the contrast that we expect for those targets. So for planets of periods of a few tens of days, we could be getting to contrasts of 10 to the minus 5 quite easily. That's too low for JWST to do, but it should be accessible for HAB worlds even in the absence of a coronagraph. And of course, the other big difference with habitable worlds is we're not going to be looking at thermal radiation from the planet anymore. Instead, we're going to be looking at reflected light, and that gives us some different information. So in reflected light, this is a range of models of different types of planets. So on the top, you've got a very classical hot Jupiter model. That's HD109733b. The reflected light bit is way over to the left there because most of that is actually still thermal emission. On the bottom, we've got a Jupiter analog. And then in the middle, we've got two flavors of a sort of 0.2 AU Jupiter. One where I've assumed it's water dominated, one where I've assumed the spectrum is methane dominated. And these are the sorts of species you will expect to see. So you can see for Jupiter, we've got ammonia. You might start to see ammonia, perhaps for some of these cooler, slightly cooler Jupiters. Then for HD189, we've got things like sodium and potassium. We don't know if they might persist to those temperatures as well. And we might still be seeing a little bit of thermal emission from some of these right over to the very longest wavelengths in that spectrum. So as you're pushing up towards 2 microns, if we get that far, you may also start to see a little bit of a thermal phase curve from these targets as well. Now, if you go further into the ultraviolet, this is why I keep asking about ultraviolet and ultraviolet coronagraphy, there's a bunch of interesting species you could potentially probe. And some things that are particularly key for cooler gas giants are things that we do see in Jupiter's atmosphere, like, for example, phosphine, but that we will not access in the infrared with habitable worlds because the cutoff is too short. We could, however, go and do it in the ultraviolet, and that the same goes for sulfur species like SO2, like H2S. All of these are relevant for hot and warm Jupiters, and again, we don't know exactly which of these will be relevant for those intermediate cases. So we'd really like to be able to probe all of these different species. And of course, clouds are absolutely key for reflected light spectroscopy. Clouds increase the albedo of giant planets, particularly towards longer wavelengths. So you can see in this figure, the cloud-free spectra, you have quite a substantial drop-off in the amount of reflected light as you go further into the infrared. This is for a Jupiter-type planet. You can see the methane just eats up all of the radiation. But if you have clouds in the atmosphere, depending on how high up they are, as they go further up in the atmosphere, they increase the reflectivity towards those longer wavelengths. And reflected light phase curves are really good probes of aerosol properties. So these are flux ratios as a function of phase angle for a range of different types of cloud. We've got magnesium silicates or a mixture of magnesium silicate, Al2O3 and TiO2. And you can see that the phase curve peaks in different places depending on what your cloud is made of. So having a phase curve is actually diagnostic of what is forming the clouds on your planet. And finally, polarimetry. If there are any Pollux fans in the audience, this one's for you. Aerosol composition affects the fraction of linearly polarized light in quite a dramatic way as a function of both phase and wavelength. So having spectropolarimetry would be a really, really useful diagnostic, again, for different types of cloud. So you can see that you get very, very different characteristic curves for something like Mg2SiO4, that's in the middle on the bottom, and Al2O3, that's in the middle, that's on the bottom on the left-hand side. So what do we want? Well, I mean, like everyone, we kind of want everything, because why would you not ask for everything when you have a massive flagship mission? But the things that we are really, really keen to state, to make this science case work, we need really good stability. We need to be able to stare at a target for 500 hours plus and know that our baseline is remaining the same to a high degree of precision, to know that what we're looking at is this tiny, tiny, tiny change in the amount of flux from the planet as the bright illuminated side rotates in and out of view. We would really like a big wavelength range. I mean, ideally, we'd want 1.1 to 5 microns. We know we're not going to get to 5 microns. We know there are thermal considerations that mean that's unlikely. But as an absolute bare minimum, we want to be going to maybe 2.5. And we really do want to go down to 100 nanometers to get all of those ultraviolet species. So I will leave you with my take-home points. I hope I've convinced you that we're not done with transits. HWO is going to be a great transiting exoplanet engine. Phase curves are a great measurement strategy. And I will also point out that whilst I've focused on phase curves, if you have a phase curve, you also get, for free, eclipse and transit. So you have all of that capability as well if you get a phase curve. So we want phase curves of tens of days covering at least bare minimum 150 nanometers to 2.5 microns. And we would like polarimetry as well. And of course, the bonus, if we fill in that kind of middle region of the diagrams I was showing you at the beginning, we can then compare these sort of intermediate temperature gas giants with the really hot ones we've seen from JWST and the directly imaged ones we're going to get with the coronagraph, which leads very nicely into Mikhail's talk that will take place after posters. Thank you very much.
All right, questions. I love that wish list. So while we wait for questions from the audience, I have a question for you, which is, we still have some time before HWO launches. What should we be doing right now and in the next 15 years to better position ourselves to understand the data we'll get of these 10-day Jupiters with HWO?
So we're talking about modeling work.
Modeling or observation or laboratory work, you pick.
So in terms of observations, one of the things I'm really keen on, which if anyone's on Hubble tax, hint, hint, we've got a handful of reflected light observations of a few of the hot gas giants with Hubble, with STIS, and with UVIS. Really hard to convince TACS to do more because they are pretty challenging. Hot Jupiters are quite black, but not all of them are black, and HD189 is a really classic example. So yes, it's hard. Yes, you might not see a signal, but that's important information. Can we have more of those, please? That would be awesome. And the other thing is we are starting to see some slightly cooler transiting Jupiters that are accessible with JWST. I think it's fair to say they're going to be really popular targets anyway. I know many of them are being observed, but modeling those and learning about those is going to be really critical.
Excellent. Other questions? I'm just going to keep on asking questions if no one else does. On the back, all the way in the back. Thank you.
It's Vincent, I can see you now.
Hi, Jonas. Can you say something about the wish list you put up? Like the very wide wavelength range, exactly why do you need the full wavelength range? And I'm not that I'm unconvinced, I'm just trying to understand where sort of the key bits are. Like why do you need the very wide wavelength range, and what about the spectral resolution? And how much could you relax any of these and still do really cool stuff versus what's super essential?
Yeah, so I mean the wavelength range, the really big wavelength range, in a way it's a little bit an either or. I think I've kind of, I think we're pretty convinced now that getting to 5 microns isn't likely. But my argument is if you're not going to go much beyond 2 microns, to do gas giants, you need to therefore go the other way. You can't not have either because you lose so many species that are really sort of important and diagnostic of what the chemistry is going on your planet. So if you're not going to get ammonia, phosphine in the infrared, then let's please get it in the ultraviolet. I think that's a really important trade-off to make. And in terms of spectral resolution, I mean, I was really intrigued actually by some of the talks earlier in the week that I'm really heartened to see people pushing towards resolutions of a few thousand as kind of baseline. That kind of moderate resolution space is really important because you don't actually lose signal, you just spread it out over a larger number of pixels. So you don't really lose anything by going to those resolutions, and you may, if you have high enough signal to noise, then you gain an awful lot, because if you've got species that you didn't expect to be there and they're overlapping and you need to sort them out, breaking those degeneracies is made much harder if your resolution is poor. And we've seen that time and time again. Going from Hubble to JWST has been such a huge leap in that respect, as well as the wavelength range. You know, K218b, everyone thought it was water to start with, because water and methane at that resolution look really similar. And you just can't sort them out at that particular wavelength. So I think resolutions of a few thousand would be absolutely ideal for this science case.
Excellent. Other questions? Excellent. Good. In the middle there.
Have you thought about if there's a TAC and they don't want to give you 500 hours, like is there certain portions of the phase curve that you'd be most interested in going after, or like subsets of this observation?
I mean, if you could envisage an instrument that had really perfect stability, you wouldn't actually need to stare for 500 hours. You could snapshot, but that will very much tie into how stable your instrument is. I mean, in fact, we did this with Hubble. Phase curves with Hubble were all because you've got this thing on a 90-minute orbit, so you have these chunks, but you have horrific systematics because of the thermal environment changes, and you have these massive ramps. If you look at a raw Hubble phase curve, you can't see any signal in it. The processing you need is enormous. And these signals, because you're talking about reflected light, because you're talking about targets that are quite a bit further away from the star, the signal is going to be a lot smaller. I mean, if someone came to convince me that the stability would be sufficient, that I could guarantee I would still see a signal with little short stares and coming back, I think I would be okay with that. So that's, I guess, another rallying cry for the instrument stability.
Great, thank you so much. Okay, let's give Dr. Barstow another hand. We are about ready for break, but before we do that, if you have a poster that is on display right now, please raise your hand. Okay, keep your hand up if your poster is on the 4th floor. Okay, and now hands up if your poster is in the technology area. Okay, everybody else, raise your hand if you're going to the 4th floor. Now raise your hand if you're going to the technology area. Okay, I will see you all there at the posters, and then I'll see you back here at 4:15 for our final round of talks. Thank you, everyone. Let's give our speakers another round of applause. It seems to me that we've lost some people from before, but I know that they're all hanging out at DCA waiting for flights. So you're all the smart ones. You're here, and you get to hear talks instead of just sitting waiting for a flight that probably can't take off because of storms. You're also in for a treat because our first speaker, Mikhail Min, who is from an organization that I will not pronounce in Dutch, but I will say ESRON instead, and Mikhail will tell you how it's actually pronounced in Dutch. Will tell us about the atmospheric characterization of cooled gaseous planets with HWO.
Thank you. Thank you. So, yeah, I'm from the Space Research Organization, Stichting Ruimteonderzoek Nederland, as we would have been before, but now it's just the English acronym. And I'm going to tell you about cool gaseous planets with HWO. As Joe has told you before the coffee break, we don't know all about them yet. We just know Jupiter and Saturn, and we are lucky that we have 4 of these planets in our solar system, right? Because we also know that they are rare. So I'm going to tell you about this SCDD that we developed with all the people that you see there. So many people contributed to this, and I think it's great. And I'm going to start with one question to you. Are we alone? And raise your hand if you think yes. And raise your hand if you think no. It's awesome, eh? It's a multiple choice question. You can do that. So in high school, I loved multiple choice tests because you could just guess. And now you are giving answers because in 15 years, when we know, you can say, I told you so, right? But these questions are a bit harder to do with yes and no, right? So these are the questions, the what and the how and the why and the where. And these are the questions that we want to answer for the giant planets. Right? What are the individual properties of gas giant planets? And which processes lead to planet diversity, if I can actually still use that term here. And so what fundamental properties determine the complexity of giant planet atmospheres? How does a planet interact with its host star and planetary system influences and wait. That's not a good sentence. How does the host star influence the atmosphere? And how do giant planets fit into the continuum of all substellar objects? So these are the questions that we want to tackle. And I'm not going to address all of them now. For that, I really encourage you to read the document that we wrote. I'm going to tell you a bit about some of them. And here are some pictures of our gas giants. And you can see that they are very different. But one thing they have in common is that they're all very cloudy. And I'm going to tell you a bit about the cloud properties and how we can constrain these. They all have different clouds. They all have different hazes. And understanding that is key to understanding their energetics and actually also their chemistry. Now, and we want to do that because we want to do comparative planetology, right? So this is, of course, a famous slide you have seen many times, I think, already. And it shows you what what Jupiter would look like if you place it at a different location, or what Neptune would look like if you place it at a different location. And we've done that. But first, let's look at the spectrum of Jupiter, right? And you see, this is Jupiter, and you see all these different molecules. You see methane, you see ammonia, you see, actually at the shorter wavelengths, you see the hydrocarbons, you see phosphine at the longer wavelengths, which is why Joe was advocating for actually going up to the really long wavelengths, because this is an important molecule to trace the chemistry. And you see all these other things. And you could ask yourself, we have been seeing water in gas giant planets everywhere, right? You see water everywhere. Why don't we see water in Jupiter? Well, there's a simple reason, and that reason is clouds. Because in Jupiter, the water is locked up in clouds. And so what would happen if you would move Jupiter to a different location, right? Oh, wavelength range. And what would happen if you would move Jupiter to a different location? And what I show you here is a model where we include cloud formation and we include the temperature structure calculations, but then we basically just took Jupiter and we moved it to 0.6 AU around the star, where it's much hotter. And you see here, this probably won't work, right? No, it doesn't work. What you see here on your left, you see the cloud composition that you would get if you would move Jupiter to that location. And you see it's mostly sulfides, zinc sulfide. There's a bit of Na2S clouds. But the water clouds are not there, because the water is all just in water vapor. And what you see in the spectrum, and I've indicated this here with blue, you see the very deep water features that you would see if you would move Jupiter to that location. And in the pink, you see actually the ammonia features that also still are there, because also the ammonia clouds didn't form yet. Now, if we move it further out, you see that the water cloud forms at some location, and actually the water features become much weaker. So you see directly, you see the effect of the cloud formation on the spectrum of the gas giant. If we move even further out, and now I want you to look at the ammonia features at 1.5 and 2 micron, and you see that they weaken because you start to form ammonia clouds in the atmosphere if you go to 2.5 AU. And then if you go to a Jupiter radius at around 5 AU, you have the very strong ammonia clouds, and below that you have some water clouds, and you see the ammonia features have completely disappeared. And this is a good tracer of these cloud rainout species. If you would even move further out, at some point the methane starts raining out, and you would lose also the features you have left here, which is basically methane. And then at the short wavelength, you see a bit of H2S. Now, the interesting thing is also that this is for Jupiter. So Jupiter has an internal heat source, which is around 85 Kelvin, right? So it's approximately the same as its irradiation temperature. Now, what would happen, and that temperature, we believe, is a remnant of the formation process, and it tells us something about the interior of the planet. Now, what would happen if we would make that 170 Kelvin? Now, what you would see is the ammonia cloud disappears, right? Because it gets hotter. And you only, and again, in the spectrum, you see that your ammonia feature reappears. And if you go to 85 Kelvin, ammonia disappears again. And if you go to 40 Kelvin, then the cloud sinks so deep that your methane features get stronger. So actually, we can use this, so the depth of the methane features and the different molecule features appearing and disappearing, we can actually use that as a tracer of the internal heat of the planet, and in that way also trace planet formation. And there's a very nice study by Renyu from a few years ago, which also shows this. Now, another thing I want to emphasize, because these are nice models. We have cloud formation, and we understand cloud formation. We don't. We don't understand cloud formation. We understand it a little bit. And one of the things we really don't understand is haze formation, which is happening because the methane in the upper atmosphere reacts on the photochemistry to form bigger and bigger structures, and it can form these photochemical hazes. But how can we distinguish between a cloud and a haze? And luckily we can if we use polarimetry. So polarization is a very interesting tool, and here I show models from Daphne Stam from actually more than 20 years ago, where she already made that prediction, that here you see models of a clear atmosphere, a tropospheric cloud layer or a stratospheric haze layer, and you see that, that actually in total light, the tropospheric cloud layer or the stratospheric haze layer are exactly the same, while in polarization you can nicely separate them apart. And that is because of their different polarization properties. And if you look at these polarization properties, you actually see another interesting thing, which is you see these wobbly features, which you would recognize as rainbows, and you see them in direct light, but actually in polarized light, they're even more pronounced. So if we have polarization of these planets and we have them at different phases, we can actually trace the composition of the clouds, we can trace the particle size of the clouds, and this will put very strong constraints on cloud formation processes. So I think this is a very important thing to have on a mission like HWO. Now, one thing I still want to talk about in the last minute that I have is some detection predictions from the nearby star sample. So what we did here is we used the standard sample of 160 nearby stars. That is typical for HWO. And then we took some planet occurrence, which you see there in blue. This is the underlying giant planet occurrence rate. And you see there as a function of planet temperature. So actually hot temperatures close there and then cool temperatures over there. And planet mass, you see how many planets we would find if we would just do our search for Earths with a coronagraph that has an inner working angle of 3 lambda over d and an outer working angle of 10 lambda over d. And you see that we would miss most of the giant planets. And that's not strange, because they are just simply out of our outer working angle. Now, if we increase the outer working angle to 20 lambda over d, or to even 30 or 40 lambda over d, which fortunately everybody from the technology already home, because otherwise they would start crying by now. But 40 lambda over d is a bit wild, of course. But you should remember that I did these calculations for 0.75 micron. So if you would actually go to 1.5 micron, this would correspond to 20 lambda over d to catch these planets. And you see that you go from, for Jupiter-like planets, you go from 10 lambda over d, where you would only capture like a quarter of the planets. And if you have this, you capture actually 80% of the planets. So this is, I think, a strong case for having a large outer working angle. And this is actually the case where you optimize the sample to look at these stars. So say you know already from radial velocity that there's a planet there. You can, of course, look at it at the moment when it's actually closer to the star, because in its orbit it gets closer, and you can optimize that. And that's another way of actually capturing these giant planets as they go, even with a modest outer working angle of 20 lambda over d, which I find modest, but others might find not. So just to summarize, I leave you here with the summary because I'm already a minute over my time. But I think it's going to be really unique to characterize Jupiter, Saturn, maybe even Neptune and Uranus-like planets. And for that, we really would advocate for as large as possible outer working angle to capture them and to look at really the family portrait of these planetary systems. I'm also actually echoing the same thing as Joe had for a slightly larger wavelength range to capture more of these exotic species that we see in Jupiter atmospheres. So thanks.
Thank you. Questions? Yes.
I'm very curious to know if we can learn something about clouds and hazes when we go to the UV.
Well, so most of these clouds and hazes have actually a very blue scattering slope in the UV, optical to UV, and I think the hydrocarbon hazes have actually also some spectroscopic signature there. So at some point, your planet will be completely dominated by hazes, simply because the opacity goes up so strongly.
Yeah. Great. We have time for one more question. So you mentioned family portraits. A family portrait would benefit from having the Earths and the giant planets in the same system. But if you were unable to get the outer working angle you wanted, presumably you could look at more distant stars to find the Jupiters. Can you remind us why it is so important to be able to do this all for planets in the same system?
Yes, yeah, sure. I wanted to actually say that. Thank you. I forgot. No. Of course, Jupiter has been really important for, well, at least this is the theory, that Jupiter was very important for life on Earth, right? Maybe bringing the water to Earth, also providing planetary defense when we couldn't yet, by keeping the asteroids out and providing the. Now we can do that ourselves, but we couldn't do it in the right? With HWO we can do planetary defense. So that's why actually I think it's important to get a whole picture of where does these Earth-like planets live, in what type of environment do they live.
Excellent, thank you. Wonderful talk. All right, our next speaker is Martin Barstow from Leicester University.
Thank you.
It sounds like it. Can you hear Martin in the back? No?
Turn your pack on.
Is there a green light on your pack? Here, this one's on.
Okay. How's that? Yeah, that's better. Okay, I have to declare that this is a bit of a career highlight for me, because I have never spoken in the same session as my daughter ever. So, and it's also a nice illustration of how Habitable Worlds Observatory has this possibility of transcending the generations. Yeah, we're in it for the long haul, aren't we? So people like me who are going to sometime rotate away, because inevitably I'm coming to the end of my career, hopefully hand it on to those of you who are going to take it forward and benefit from all the effort that everybody's putting into it. Anyway, I haven't got long, so I'm going to crack on, but I can also thank Andrew for giving part of my introduction, so it will save me a little bit of time. So I felt like a little bit of a fraud when I put this talk in, because I'm not talking about exoplanets really, I'm talking about white dwarfs, which is my primary interest and the reason why I never speak in the same session as Joe usually. White dwarfs are actually intrinsically important for all kinds of astrophysical reasons, which I've listed here. And we wrote an SCDD about this, and I have to acknowledge C.E. Xu, Patrick Dufour, Andrew Buchan, and Erica Laborde, who actually did the real work on this. And I just happen to be talking about it because I'm the only one who was able to come. So I'm going to talk about a couple of things among the massive importance of white dwarfs. And this is something introduced by Andrew earlier, the idea that white dwarfs are actually eating exoplanets for breakfast. Also, they're very important for study of matter under extreme conditions. I'm not going to say too much more about this, but if you look at the plot on the right, this is an illustration how under certain theories of gravity, the fine structure constant shifts around and actually perturbs the spectrum of a hot white dwarf star according to the gravity. We've never detected this with Hubble. We've observed a half a dozen stars, and the problem there is that we can only observe a half a dozen stars with enough signal to noise to even attempt this. And Habitable Worlds Observatory will give us a huge platform on which we can do a proper statistical, precise study of what's going on in the atmospheres of white dwarfs. But the thing that I'm really going to talk about is this idea that white dwarfs are accreting material from the exoplanet systems that surround them. So as Andrew said, we have compact objects, strong gravitational field. The important point that I think maybe he didn't mention that I'm going to add to that introduction is that the residence time for heavy elements heavier than hydrogen and helium in the atmospheres is very short indeed. In a hydrogen atmosphere, it's like years to days to years. In a helium-rich atmosphere, it's only a few tens to a few hundreds of years compared to the whole billions of years of a white dwarf lifetime. So if you see something in the atmosphere, then it shouldn't be there. But there are mechanisms that modify that, one of which is accretion, so sucking in the material from outside. Also a process called radiative levitation in the hot objects that actually holds up material and stops it sinking down. So we just need to be aware of that complication. And there's lots of evidence for debris around white dwarfs. Here are a few examples of full optical and infrared spectra. And the white dwarf spectra are on the left, as I look at them now. And the spectra of the debris is on the right in the infrared. So there are lots of disks surrounding white dwarfs. What happens to that material? Well, it eventually ends up in the atmosphere of the star. There's a really good example, actually historically interesting, which is Van Maanen's star. This is a modern spectrum of that star, but even in the early part of the 20th century, it was realized that this was a peculiar object because it had polluting material in its atmosphere, long before we really understood what white dwarfs were. UV spectroscopy is going to be really important for us because the UV is where a lot of the important lines of important elements like carbon, silicon, sulfur, nitrogen, molecular hydrogen, iron and nickel, I could go on. So this is where habitable worlds becomes essential because it reaches the wavelengths that we can't get in any other way. So although our beautiful 30-meter telescopes, which will come on stream in the next few years, at least in the case of the ELT, will give us fantastic data, they will not be able to detect the important elements that we actually want to see. And it's all about statistics. We've done some of this work with Hubble. Hubble is fantastic, but it's not big enough. We need many, many objects to actually do a thorough statistical analysis of the various compositions that we can infer of the exoplanets from the white dwarf atmospheres. And we need HWO to build that large sample. And I'm sure many of you will probably sympathize with me. When you write a proposal and you say, I want to observe 20 stars, it gets rejected and somebody says, why did you want to observe 20 stars? How many stars do you really need? Oh, you could do it with 10. Or maybe you need 100 and you're only asking for 20, so we're not going to give you any time at all. So if you've ever suffered from that, put your hands up. So what we've tried to do is quantify how many stars we need as part of our SCDD. And I think this is the real point I'm trying to get to in the last couple of minutes that I've got. Firstly, we need high resolution. The plot on the right-hand side of the screen there shows how a complex of ion lines changes as you increase the resolution of the spectrograph. I would point it out with the laser, but the laser's kind of weak. So I'll just turn around and try and wave at it. So you look at the blue curve, which is 15,000. Well, you don't really see the complex. You don't separate those important individual lines. 30,000, well, you're sort of getting there, but it's still not enough. So we really need to be at least at 60,000 resolving power. But actually, really, we want about twice as much as that. And so that's for us an important driver, that very high resolution. And we've heard a few talks over the week actually express that for things like interstellar studies as well. So high resolution is very important, but we also need to observe a lot of stars. In this set of plots, the really important things are the two plots on the right-hand side. The left hand is a distribution of possible mass fractions of water in the bulk composition of some of these exoplanets as we see it in white dwarf atmospheres. Now, there are some hypotheses here. Do these objects have water? Is there a population with water? Well, we can determine that. And the probability distribution on the right, which is the top panel, actually expresses that as a function of the number of polluted white dwarfs that you observe. So if we want to say with some confidence that there is a population of water-bearing objects, and obviously we all accept that water is very important in our search for life in the galaxy, then you need to observe around about 150 or 160 objects before you get to a reasonable probability above 90% that you can say, yes, this population exists. Another thing we want to look at is trace elements within the core composition of exoplanets, because that influences things like plate tectonics, the behavior of these planets as a whole. This is not quite as demanding, so that's the bottom right plot, which looks at sulfur versus silicon-rich cores, which behave completely differently, and therefore give you different kinds of habitable worlds, or potentially habitable worlds. So to get up to 90%, well, we need to observe about 40 to 50 of these stars. So we're now getting a feel for, what does the sample size need to be? But these are just two examples of the kind of thing we might look for. There are many other things that we might want to learn from these populations, and this is the tool for doing that. So this is my last slide. Courtney would be pleased to know I've got 40 seconds left. I'm looking at the countdown. So we've drawn all that information together to essentially put our list of demands in, like everybody else. So we want high resolution. We also want that high collecting area to actually give us the signal to noise that we need on the objects. But most of all, we want observing time to observe a lot of objects. And of course, big glass gives you lots of objects in relatively short time as well, so it's a very efficient way of collecting that data. And that's all I have to say. But thank you for staying to the bitter end for the graveyard shift. It's really nice to see so many people in the audience.
Thank you. All right, what questions do you have?
Hi, Megan Jaluka, University of Washington. That was a really great talk. And as someone who's interested in atmospheres, any way we can start to think about what's going on at the surface-atmosphere interface is fantastic. I was just wondering, it's like my understanding that as a star transitions from its main sequence lifetime to becoming a white dwarf star, that can be a pretty chaotic time for the terrestrial planets close to it, like Mercury, Venus, even Earth. And so I'm wondering, for those planets that are left over during its time as a white dwarf that can actually be then eaten by the star, is there going to be a population bias in the possible compositions?
You can't rule it out completely, although there's less chaos than you might think. But what happens is you tend to get a lot of migration outwards. So although we might fondly imagine that the Earth will get swallowed up when the sun becomes a red giant, that's probably not going to happen, because it's not like the sun goes from sun to red giant instantly. The process creates a sort of dynamic movement in the system. There are a lot of studies going on. In particular, there's a guy called Dimitri Veras who works at Warwick University, who is really the guy who does this stuff and simulates all these changes. So I think it's going to be more coherent. But you're right, which planets are we going to accrete over time is an interesting question, because we might accrete several, and we might just be observing at one instance when, let's say for the sake of argument that Venus and Earth have gone, and we might actually be looking at Mars falling in. Who knows? So there are some statistical uncertainties in there, and that's another reason why we need to observe a lot of objects.
Excellent. I saw a question in the back, too.
Brianna Lacey, UC Santa Cruz. By the time you get to the white dwarf stage, do you retain any information about which populations of the galaxy these stars came from?
Sorry, I'm not...
Could you compare,
So the population of the progenitor star?
Yeah.
Yeah, okay. You can infer that from the timescales, because you know from the mass of the white dwarf what the progenitor mass was. So you can then sort of work back and understand what the time scale for the lifetime of that star was. And there's a lot of work going into sort of initial final mass relations, which are pretty well determined now, that allow you to do that. So yes, you can make that inference.
Okay, any other questions? In the back, yes.
Oh, it would be you. Another white dwarf guy.
I promise to be gentle. So at these very low galax magnitudes, does this also open up for trying to do some detailed studies of nearby very cool white dwarfs too? How do you know roughly how cold we can get for something that's like in the local neighborhood?
Well, I think in principle we can go right down to the absolute lowest temperature that's available to us. Of course, white dwarfs evolve over billions of years, and we use the population of the coolest white dwarfs to infer an age for the galactic disk, and that's about 3.5K. So we should, with an observatory this big, we really should be able to see those stars. And we can almost do it with Hubble, but not quite.
Great, thank you. Let's thank Martin again. Okay, our next speaker is Dr. Kara Bregman, who will be telling us about geochemical habitability.
Thanks, everybody. We here okay? Okay, good, thanks. All right, thanks everybody for hanging in here, the last session of the day, and especially to everybody online. So this is a picture of the newest continental crust on Earth, at least at the time that the photo was taken. Now, volcanoes and their lava is how a planet makes new crust, and that crust is where life as we know it can live. You can also see in this photo these beautiful gas plumes. Lava also carries volatiles from the interior of the planet to the surface, where it can be added to the secondary atmosphere. We are releasing things like water, carbon dioxide, and sulfur species. So the composition and the abundance of that gas is directly related to the composition of the carrier lava, which is in turn related to the composition of the silicate part of the planet. And that way, the silicate mantle helps to influence the composition of the parts of the planet that we have the potential to observe, the surface and the atmosphere. So I know we all understand that that's important, but you probably still wonder, why geochemistry, why now? Isn't it a little too early to be thinking about this? And I think it's actually approaching too late, because the amount of time that we have to get this information that we need to influence our observations is running a little bit short now. So we already know that a lot of our atmospheric observations include biosignatory gases that could be produced abiotically. We need to have an understanding of the geochemical composition of the planet in order to rule out a geologic or an abiotic source for those species. Also, although I'd like to be optimistic about it, I think the possibility of us getting a composition of an exoplanet's surface that is truly detailed enough for us to know something relevant geologically is probably several decades away. So in order to interpret our observations of these atmospheres, we need to have some kind of geochemical context to fit it in. And geochemical experiments can help us bridge that gap. So that's where I come in. I'm an experimental igneous petrologist, which means I actually make magma in the lab. I use this apparatus called an end-loaded piston cylinder, which allows us to simulate the temperatures and pressures appropriate for the upper mantle and crust of Earth and Earth-sized planets. So I've already done this for a couple of different relevant studies. So first I'll mention that I have done a solubility study looking at molecular hydrogen in a magma ocean. Our important finding here is that rocky planets can produce enough water through normal reactions between their magma ocean and the overlying molecular hydrogen-dominated atmosphere to account for Earth's current water budget or even more. And this is really an important result because this lowers the barrier to habitability for rocky planets beyond our solar system. We're no longer reliant on a chance encounter with a comet to come by and make up the water budget we need for a habitable planet. We're just removing the luck from that equation. This paper should be out in the fall, and there's some tasty tidbits for modelers, so please be on the lookout. Currently, I'm the co-I for a NASA ICAR grant where we're looking at the solubility of phosphorus in exoplanet lavas. Now, phosphorus is this kind of rate-limiting element for life as we know it. We want to know what kinds of phosphorus abundances in stars and planets is necessary to ensure that phosphorus cycling continues for millennia. But for today, I'm going to talk about experiments that are much simpler than those, that are much more basic. We've already conducted some of these in past years, and I'm going to conduct more of them in the future. We're all very familiar with these questions, so I want to bring up one that's a little more pointed. Is a star likely to host a planet that is habitable to life as we know it over the long term? So in order to get at a true eta Earth and to better understand and pick our observations for HWO, I suggest that we should consider whether a planet is geochemically habitable. Does it have the right surface conditions to support life as we know it? So this is not only bioessential element cycling, but does the planet even have a solid surface? Does it have the right amount of water, not too much, etc.? So by the end of this talk, I hope to convince you that geochemical habitability is an important consideration when we're thinking about our exoplanet observations. So you're probably wondering how I get to the exoplanet compositions I need to do these experiments. And apologize to everyone who has had to see this plot for the past 5 years. Hopefully you just understand it better and better every time I show it. So here I'm showing a plot of the FGK stars in our nearby galaxy. I'm showing molar abundances of iron, silicon, and magnesium. Here they're shown in black with our star in the gold star. And then these thick gray lines are showing areas of equal cation ratios. But what we're interested in is a population of possible bulk silicate exoplanets. So to come up with that, we're going to translate these compositions of stars to possible planets by removing a portion of iron, assuming that's being segregated to the core. You'll notice that all of the points moved over away from the iron apex. And I can do the same thing for our star. And then I can show you what we think is the current composition of bulk silicate Earth. And you notice that they're not the same. There's a lot of things that can happen to a planet. But also I want to note that we did not bootstrap this translation to Earth. We want to make as few assumptions as possible, so we're not biasing this type of data visualization of the compositional space. So we looked at this plot, and we picked out 2 hypothetical compositions for an exoplanet to do our experiments on. One, the orange one, has a higher magnesium to silicon ratio than Earth, and you can see that it is closer to the magnesium corner of that diagram. And we picked the other, the purple one, which has a lower magnesium to silicon ratio than Earth, but a higher calcium to aluminum ratio. So here I'm just showing you the same data plotted on a similar plot. We're zooming into the top corner. Now notice that our 2 hypothetical compositions, they're at the edges of the point cloud for the inset, but in the larger diagram, they're following about the same iron to magnesium ratio as Earth. So these planets, they're not really that different from Earth. You can see that there's a pretty big spread in the potential compositions of planets out there. And I want to emphasize also that we're not picking a particular star or a particular planet to simulate here. We don't think that's the best way to go at this. The composition space is just too big. So we put those compositions into our piston cylinder. We take them up to temperature and pressure. After we quench, we're left with these beautiful minerals in the melt, which is analogous to the mantle of that exoplanet and the magma that we would extract from it. So I'm interested to know, no cheating if you read this paper, which of these planets do you think were geochemically habitable or all? So who thinks the orange one is geochemically habitable? Okay, who thinks the purple one is geochemically habitable? You are correct in being very hesitant to raise your hand because you cannot tell from this plot. Okay, so what we found is that our orange planet, it was probably geochemically habitable. We have a mantle mineral assemblage and melting relationships, a solidus, that's very similar to what we see for Earth. However, this purple planet, it is decidedly not geochemically habitable. Why is that? When we look at our run products from our experiments, we see that the density contrast between the minerals and the melt are telling us that probably this magma isn't actually going to erupt. It's most likely to stall, cool, and crystallize in the crust, so it's not actually coming to the surface. That means that it's not releasing a lot of volatiles from the interior of the planet to the surface, so that's going to affect what our secondary atmosphere observations look like, or actually probably not affect them, rather. And it's also not making any new crust on that planet. No new crust means that also plate tectonics is probably suppressed because we're not having that decompression melting that's helping to drive spreading centers. And the end effect of all of this is that the cycling of bioessential elements, including phosphorus, is probably severely restricted. This means that any of those elements that life needs to access to live is going to be buried over time, and then there's not a clear method to bring it back to the surface for them to use it again. So this really highlights the difference between a planet that can give rise to life in an instant versus a planet that's capable of supporting life over the long term. But it turns out for this planet, the news is actually even worse. Based on the melting relationships we see, the pressures and temperatures, solidus, probably this planet is just going to be a persistent magma ocean. So one of these is probably observable. The other, I'm not sure how we would tell that there was no element cycling definitively. So this emphasizes how important it is to these kinds of experiments to discriminate between these kinds of outcomes. But one of the most important findings of the study is actually none of our geochemical models can predict these results. So I'll say that again. None of our geochemical models are able to predict these results, not even close. In fact, we chose this composition, the purple one in particular, the problem child here, because we wanted to encourage the crystallization of a certain type of mineral, and it did the opposite. So even the petrologists, can get it wrong sometimes when we're trying to predict. The problem is, of course, that all of our current knowledge is based on our geochemical understanding of Earth and the compositions that we started with in our solar system. So experiments are crucial for us to not only improve our models, but also to pick the HWO targets that are going to be the most fruitful, that are most likely to have planets in orbit that are able to host life as we know it over the long term. So I hope I've convinced you that geochemical habitability is an important parameter for choosing HWO targets and for calculating eta Earth. We have the QR code at the top here. It's a very quick read because I have a grant proposal out on the same topic, so I wasn't sure how specific to be in this public document, but I will flesh it out a little bit more after I hear the results. More importantly, I want to advocate for a coordinated multi-lab campaign to explore the composition space that I've shown you today. Experiments take a long time, they're expensive, they take a lot of man hours, and we have a lot of work to do before we can give you guys the data that you need. So experiments, in short, are really important to move our geological understanding outside of our solar system, important for improving our models, and then downstream, important for helping us to better predict which stars are most likely to host life as we know it. So if you're interested in these experiments, you can hit the QR code at the bottom and read the paper. And lastly, I'll note that at a conference last year, I was asked what I need to complete these kinds of experiments. I said I needed money, time, and people. Usually the answer for this question that we all get. But I'm happy to announce that I'll be accepting students in 2026. Starting in January, I'll be beginning a new position at the University of New Mexico as an assistant professor. So if you or any students you know are interested in doing these kind of exoplanet experiments, please reach out. Thank you.
Congrats on the new job. Great. Questions? I see a couple. We'll start with Renyu, and then we'll go to Camilla.
I'm curious, when you predict that the density contrast of between the melt and the solid would not allow the volcanism to happen, do we need to consider, for example, the heterogeneity inside the planets or the inclusion of volatiles in that kind of estimates?
Sure, we didn't account for that in this particular estimate, but again, we are trying to look at the most basic scenarios, the most baseline scenarios to see what could happen. But those are important considerations, especially for planets that we have better geochemical data for.
Hi, here. I missed something. I didn't understood you quite well. What do you mean that the planets will have a magma ocean like always? Planets will cool with time, so
Yeah, so when we looked at just the run products and their compositions, we realized that probably the bioessential element cycling would be cut off. But then when we looked at the actual temperatures and pressures of melting, the location of the solidus for this planet, we realized that it was always going to be above the adiabat. So we were always going to have melting rather than solids.
But at some point it will cool down, right? You are
at some
losing
point,
energy.
yes.
Okay.
Yes.
Right. Other questions in the back?
Your suit is amazing, by the way.
Svetlana Berdugina, Switzerland. Thank you so much for interesting talk. Can you explain a little bit why in calcium aluminum case there is no tectonics and all other effects? I didn't understand that.
Oh yeah, so this is, again, what we were inferring based on the density contrast between the minerals and melt. We're taking the simplest possible case and just looking at the, actually the migration velocity of the melt as it percolates through the different mantle minerals. And we found that it was, if I'm remembering correctly, 30 or 50% more slow than we see for Earth-type melts.
Fascinating. All right, I have a question I'm going to sneak in, which is, we have multiple terrestrial planets in our solar system. What can observing the other three help us in terms of understanding plate tectonics and geochemical habitability?
For sure. They help us understand basically that a lot of different things can happen to a planet. That's one of the reasons why we didn't want to bootstrap our conversion from stars to planets, because there are so many things that could happen. So we think it's more interesting to look at the range of possible compositions, because even though the geologic histories and the evolution histories of the other planets in our solar system are pretty different, they're still based on the same nebular building blocks that made our star. So there is probably, very likely, a basic correlation between the compositions of the rocky planets and the star.
Thanks. Let's thank almost Assistant Professor Bergman again. Right, our next speaker is Thomas Stuber from the University of Arizona.
Hi, can you hear me? Does it work? Yes? Okay, it's all the same for me here. Yeah, yeah, I'm Thomas. I'm from the University of Arizona, I'm a postdoc there, working with Virginie Farmas-Gorka and Steve Oertel, and also many collaborators across the country and mostly in Europe, apart from that. Yeah, thanks for sticking around. This will be another dust talk. It's about hot exosodial dust and its effect on HWO's performance in finding exo-Earths. So this is about debris disks. My research focuses on debris disks. So what are debris disks? Debris disks are circumstellar disks of dust. And they're usually characterized as being gas poor. So in contrast, for instance, to their progenitors, protoplanetary disks, which are very gas-rich, and they are optically thin. So they are very tenuous, very faint in observations, distributions of dust. Where does the dust come from? It comes from planetesimal fragmentation, which you can see on this nice artist image on the right. So in a planetary system, as we hope, you usually have some exoplanets, but you also have a lot of minor bodies, kilometer-sized bodies. Like in the solar system, these would be asteroids, comets, Kuiper belt objects. And those objects collide and get shattered into fragments. These smaller fragments collide again, producing even smaller fragments. This happens again and again. And so the kilometer-sized planetesimals are ground down to millimeter, micrometer, partially sub-micrometer-sized dust. So we have debris disks around white dwarfs, as we heard two talks earlier. This talk focuses on debris disks around main sequence stars, solar-like stars, and also A-type stars. So how does a debris disk look like in observation? So this is one of the most modern and maybe most beautiful images of a debris disk around the Fomalhaut system, 8 parsecs away from us, very close, imaged by JWST MIRI at 25.5 micrometers, so in the mid-infrared. And as you can see, there's a lot of stuff going on, a lot of structure, rings, gaps, multiple rings, smooth distributions. So debris disk researchers categorize the dust into 3 different categories. So, and they're not all the same. And we use temperatures to do that. So at tens of AU, up to hundreds and partially thousands of AU, there's the cold dust. Cold means something about 50 Kelvin is a good number. And because it's so cold, it goes in the far infrared in the millimeter wavelength region. Then there's a second type of dust, which you call warm dust. or also habitable zone dust, or exozodiacal dust, in reminiscence of the solar system zodiacal dust that produces the zodiacal light, which you can see in very clear nights. So this warm dust resides somewhere roughly between 1 and 10 astronomical units. Warm means about room temperature, 300 Kelvin. Because of the warmer temperature, it glows in the mid-infrared. And then there's a third category, hot dust. Hot dust is closer than 1 astronomical unit to the host star. And because of this high proximity, close proximity to the central star and its high temperature, it glows in the near-infrared mostly. And this talk is about this hot dust. And this is also where we leave the realm of pretty images. So in this image on the left, all of this hot dust is behind those black pixels in the center where this James Webb image is just saturated. So the mostly used technique to observe hot exozodiacal dust is long baseline interferometry in the near and mid-infrared, and it does not produce pretty images usually. So this is about this hot exozodiacal dust. It has been found around 20% of the main sequence stars surveyed, and it has been found around diverse stellar stars with diverse stellar ages, from young stars, 20 megayears, just at the start of the main sequence, up to giga-year-old stars. It has also been found around diverse spectral types, solar-like G-type stars, up to A-type stars. The dust is relatively faint compared to the star, roughly at the percentage level, fractions of a percent up to multiple percents. And this dust is a possibly variable phenomenon. What do we know about the dust properties? So the dust is close to the star, closer than 1 astronomical unit. Thereby it is very hot, with temperatures of 1000 Kelvin and more, reaching up to the sublimation temperature of the dust grains. The dust grains are also very small, sub-micrometer in size. We don't know much about the dust composition. What we know is that silicates cannot, I repeat, cannot dominate the dust material because we lack mid-infrared emission. So these properties pose decisive challenges in explaining this phenomenon, because such small dust grains so close to a bright matrix sequence star should either sublimate rapidly or be blown up by radiation pressure, both happening on a timescale of days usually. So there are multiple theoretical efforts to explain this, but as of today there's no single theory that consistently explains this phenomenon around the diverse stellar ages, around the stars with diverse stellar ages, diverse spectral types. So we don't really know what's going on there. So that's all very nice. It's a mysterious astrophysical phenomenon. Someone should figure it out. Okay, cool, next talk. Why should you all care about this? Why is it interesting for you, even if you're interested in exoplanetary atmospheres or something else? So this dust can affect HWO's performance in finding exo-Earths. So the dust grains are small, sub-micrometer in size. So they have roughly the same size than the wavelength we're interested in. Half a micrometer dust grain, it's 500 nanometers, exactly visible wavelength range. Those dust grains scatter very efficiently stellar light. So, but the dust distributions do not sit on top of the star, exactly on top of the star. They are located at a certain distance of it, something like 0.1 AU, 0.3 AU, up to 1 AU roughly. So they're located at fractions of the inner working angles of coronagraphs, partially at the inner working angle of coronagraphs. There they cause increased coronographic leakage, and this is something you usually don't want to have if you want to find an exo-Earth. Second, the dust might migrate through the habitable zone, either in or outward. So if the dust distribution is homogeneous, it raises the noise floor, causing us to observe longer, to pull out the exo-Earth out of this noise floor. But It could also well be, and theoretical suggestions suggest, theoretical efforts also suggest that the dust distribution might be heterogeneous. So you introduce structure in your habitable zone that you then have to differentiate from your hopefully to be found exo-Earth. So the dust can add noise and confusion to your observations. So, as said, we don't really know what is going on with these hot dust distributions, so it's hard to mitigate any of this. And actually, you can help us trying to solve this problem. How can you do this? With other observations. So either, if you have a fancy idea of what's going on there, please reach out or write a paper about it. If you keep it to you, write it. We would be happy to hear new ideas. If you have James Webb NIRSPEC observations, something like 2 to 5 micrometers of main sequence stars, and maybe you even see a near-infrared excess, please think about hot exozodiacal dust. If you don't know what to do with your near-infrared excess, please reach out. And lastly, Roman coronagraphic observations. So all of that will not only affect HWO, it will also heavily affect Roman. So in fact, Roman will be the first instrument that will be able to perhaps directly image dust in the sub-micrometer sized dust grains in the habitable zone, and it will also suffer from coronagraphic leakage. So I know about the white papers, but if you have kind of some power about Roman observations, please point it towards a star that has confirmed hot exozodiacal dust. Please also point it to a star that has been surveyed for hot exozodiacal dust, but where no dust has been found, so we have a control group. I know Roman is a technology pathfinder, but it will also be the very first visible light, high contrast image in space. So it will also be a science pathfinder in this way. So, as a quick summary, there are sub-micrometer sized dust grains in the sub-AU vicinity of main sequence stars. It's called hot exozodiacal dust. We have super scarce information about demographics, variability, and the physical processes governing the dust distributions. These dust distributions might reduce HWO's performance in finding exo-Earth drastically. So before we have figured this out, every estimate on the HW science yield in finding those exo-Earth is highly uncertain. Thank you.
Roman sensitivity to hot zodiacal dust compare to what we expect to see with HWO in terms of what we need to know about various disks?
So the Roman sensitivity will be lower. We expect that the dust is, so we have a limited sample of dust, and all estimations regarding this have very large error bars. We expect that Roman will see it more or less immediately. So if it doesn't show up, it tells us a lot as well, but it should show up.
Great.
It will show up. Yeah. So
Other questions? How much structure? Oh, I see a question over there. Oh, okay. Well, Brianna can have the mic, and she'll phrase it better than me, I'm sure.
Brianna Lacey, UC Santa Cruz. When you say it can be clumpy, what spatial scales clumpy and might trick us into thinking it's a planet, or clumpy and would just confuse us about our planets?
So we don't really know what's going on. That's the point. What could be just an idea. So exocomets are discussed as a possibility to dump dust close to a star. This would be happen very localized, and the small dust grains then would be blown out. So it's not like that there's probably a point source in the habitable zone sitting there. It's something more like a stream going through. That's what I can think of. But, well, we don't really know what's going on. So, yeah.
Any other questions? Can you say anything about the power of multi-wavelength observations? So say we don't yet have information about the hot dust, but we're able to constrain the warm and colder dust, and then we have hot dust information for other disks. Do you think it's possible that we could do a decent job predicting which disks might therefore have lots of hot dust based on what we've learned about general trends, or is it all going to be really different from star to star?
So from the demographics, let's say, as of today, the hot dust is not correlated, or at least very, very, very tentatively correlated to warm and cold dust distribution. So unfortunately not. So yeah, Roman will help with that. It will give us more information, more sensitivity in the visible for the first time. So Hubble hasn't seen any of this. Either the stars just saturates everything or the coronagraphic mass blocks out everything.
Great, thanks. If you have other questions, go ahead and put them on Slack, and let's thank the speaker one more time.
Thank you.
Yes, it's on. Oh, yeah, I can hear that.
Perfect. Our next speaker is Nicole Wolf from the University of California, Santa Cruz.
Thank you so much. I'm Nicole Wolf. I'm a graduate student at UC Santa Cruz, and I'm excited to tell you all about my retrievals with correlated noise. I just want to thank all of my collaborators and mentors for the support, for making this project possible, and everybody else who has helped with this. So I won't belabor this point too much. We're all familiar with this science case. I've been looking into modern Earth analogs for my retrievals, but I just want to point out the diversity of features in a spectrum of modern Earth. We start out with a very deep ozone absorption feature in the UV, followed by a scattering slope affected by aerosol opacity. Then we have some very narrow oxygen features, some very broad water features, and finally, a little bit of CO2, only enough to set an upper limit with low resolution spectroscopy. And we're going to get this spectrum ideally with direct imaging, which has this advantage of producing nice movies and animations. We're looking at two IFU data sets from GPI and CHARS. And these aren't the typical movies of a planet going around its star with time. You'll notice that each frame is a different wavelength. And while the planet remains in one position across wavelength, the background scales radially outward and even grows with wavelength. And this is from a source of noise we refer to as speckles. These are image manifestations of error in the wavefront of light. And these are a source of chromatic noise. You can imagine they grow radially and might even pass over the planet, making it more difficult to detect and characterize the planet in question. From the ground-based observations, these speckles primarily come from turbulence in the atmosphere and can be corrected with adaptive optics and post-processing techniques. But for space-based observations, we might get speckles from any polishing errors on the mirrors of our optics, from vibrations over time, or from the way we do spectral interpolation of IFU data. And the important point here is that speckles are a source of spectrally correlated noise, coupling adjacent points, meaning they're no longer independent from their neighbors. We can visualize this with a simple cartoon here, where in the movie we saw the planet remained at the same place at each wavelength. The light from the planet is dispersed and we get this spectrum on the right. What a speckle does is it hits a planet at one specific wavelength, manifesting as this bump in the spectrum over some characteristic length scale, and coupling light from the speckle and the planet over that length scale, modifying the flux that we measure. We can imagine a different scenario where the speckle travels at a different rate across the planet in wavelength space. So now it's moving much more quickly in wavelength space, resulting in a smaller Gaussian bump that I've conveniently aligned with the oxygen A-band absorption feature. And when we add the flux from the planet and speckle, we get a modified absorption depth. A more realistic example would be multiple speckles, maybe not quite this many, all hitting the planet at different wavelengths, resulting in a background speckle field. And I'll point out that these speckles can sometimes be negative if they come from errors in our PSF subtraction. And because these speckles are Gaussian distributed in wavelength space, we can model them simplistically using Gaussian processes. And this has two important parameters, an amplitude, which is connected to our signal-to-noise ratio, and a length scale, that width in the spectrum across which the speckle passes over your planet. We can use Gaussian processes to generate several random realizations of the speckle field. So it might look something like this, or it might look something like this. Depends how we roll the dice. There is a lot of precedent for using this framework to fit for speckle noise in giant planet and brown dwarf observations, both from the ground and now with JWST from space. And there's a good reason to consider this when we're running retrievals in direct imaging datasets. It has been shown that forgetting to model the correlated noise in the dataset both biases and artificially narrows posterior distributions. This comes from a foundational paper from Greco and Brandt that I would encourage everyone to read. We can see in this figure, when we fully model the noise, as shown on the top, the best fit model in retrievals is quite close to truth. And the confidence interval of the posterior is what we would say realistic. When we only include the diagonal terms of the matrix, not including the full model of the noise, we see our best fit model is quite far from truth, and our posterior distribution is narrowed near the best fit model and maybe even double peaked. It looks quite strange. And this is the motivation for my work. Most retrieval studies for HWO have not accounted for speckle noise, even though doing so can bias and artificially narrow posterior distributions. So for my work, I simulated reflected light spectra, both with and without speckle noise. You can see the case with speckle noise by this characteristic oscillation over some length scale. And then I ran spectral retrievals using RFAST. We've heard a lot of amazing work using this code already at this conference. You're watching RFAST right now converge to a best fit model using simple 2-parameter retrievals. We can see it slowly fit this water absorption feature around 1 micron. I'm excited to share some results that represent what we might expect from speckle noise in spectra. To start off, I'll be showing corner plots for these 6-parameter retrievals. I'm retrieving 3 bulk parameters, pressure, radius, and albedo, and 3 atmospheric parameters, oxygen, water, and carbon dioxide. And I'm running these for this corner plot at an SNR of 10 and the fiducial resolutions of 7, 140, and 40. And we can zoom into one of these distributions to see what happens if we forget to include the full matrix in retrievals. On the left, our distribution is both misleadingly precise and inaccurate, whereas on the right, the distribution with the full matrix is more realistic. This is nothing new. This is a replication of the Greco and Brandt result, but for Earth-like spectra. From now on, I will assume that all retrievals with correlated noise contain the covariance matrix in the likelihood calculation. The next lesson here is that posterior distributions broaden with a decreasing length scale. So there's this inverse effect. We can zoom in to a parameter once again and see that the narrowest posteriors correspond to the longest correlation length scales. This is a mathematical effect of correlated noise, so this is a good validation that it's incorporated well into our retrieval framework, and we're getting back what we expect. But you'll notice that in this case, the shortest length scales of correlated noise produce the most uncertainty on our measurements, which is a really key takeaway. You might have also noticed that correlated noise at these shortest length scales matches the width of certain absorption lines at low resolution. For instance, the oxygen A and B bands are roughly 10 nanometers, and these broad water features are closer to the order of 50 nanometers. So the question I wanted to start asking, which is nowhere near complete, is whether correlated noise can bias our retrievals when the correlated noise is at these length scales. So I find a tentative bias in the posteriors, especially for oxygen at this 10 nanometer scale. So we're seeing the two posteriors, one for uncorrelated noise and one for correlated noise. The uncorrelated noise seems pretty centered on truth, which is the white line, whereas for many parameters, correlated is skewed in some direction. A more statistical thing to do is run this across multiple random realizations of the noise. So what I'm plotting is the best fit value for oxygen abundance across 10 random realizations. And for uncorrelated, we see this oscillate across the true value. Across 10 instances, this averages out to the correct result. You see the dashed purple line is quite close to truth. When we do this for correlated noise, we see some systematic bias towards lower oxygen abundances. I don't completely understand why it's lower. We see one outlier near the bottom. And I wanted to dig deeper into this. So I compared this to correlated noise at a longer scale. I, again, have been running this for multiple instances of the noise to try and build up a statistical sample, though we're nowhere near the statistical number of 25. I find that at 200 nanometers, this bias disappears. So clearly there's some connection between the systematic noise we're adding and the length scale of the feature we're trying to detect, which is oxygen. So you might be wondering what physical effects can produce correlated noise at different length scales. The simple example I showed of a speckle coming in and hitting the planet at a specific wavelength results in a correlation length of on the order of 200 hundreds of nanometers. It's quite long when you're near the inner working angle for an Earth-Sun observing scenario. But we know a point spread function can be chromatic on shorter length scales. I'm just showing a good visualization of this here for the GPI IFU. What we can do instead is look at the optical design of HWO, look at where all the optics are. We know that for complicated wave optics reasons, aberrations, polishing errors on mirrors that are closer to the focal plane are harder to correct with a deformable mirror, and these aberrations can result in shorter length scale correlated noise. So instrumentalists know how to do very smart things and correct for this for specific optics, but I just wanted to highlight one reason we might have correlated noise at these shorter length scales. What we can do is potentially add a second deformable mirror. There's a lot of work going into this for Roman CGI. The main takeaway here is that PSF chromaticity produces correlated noise at these short length scales, and we've seen from retrievals it both widens posteriors and potentially biases our results. So what is the path forward? I'm a little bit over time. I just want to highlight that this will be a limiting noise source for HWO. There are brilliant instrumentalists who are optimizing the instrument with this in mind, but there's a lot of work to do in the short term. For one, we can perform detailed trade studies that connect science requirements to designs of the instruments. In the long term, we need to remember to measure spectral covariance in our data and include it in retrievals, which is not something trivial to do. There's a lot of work going towards this for JWST. And I'll end with the conclusions. I just want to solicit collaboration on this project. I would love to chat with anybody else who runs retrieval trade studies and would like to start considering correlated noise in their retrievals. Thank you.
Questions? In the back, Amber.
Yeah, sorry for making you come all the way back here. But thank you so much. As a fellow retrieval modeler, I am both intrigued and terrified about what I'm going to do, but thank you so much for bringing all of this to light. So my question is, for moving forward and sort of improving being able to model correlated noise, what, in your opinion, is the best way to sort of mimic or incorporate the effects of these speckle patterns? Is it at a spectral level, or is it really like in the MCMC, you know, adding some likelihood, additional likelihood functions for it or something?
Yeah, that's a great question. We should definitely chat more. But the two things I'm doing are adding noise, physically injecting it into the spectrum using Gaussian processes, and then updating the log likelihood calculation to include a full matrix for that noise, which takes a little bit more runtime, but not by a huge factor. There are different ways we can parameterize correlated noise. For instance, I'm kind of injecting it globally across the spectrum, but you can imagine injecting it at specific regions, for instance, where the chronographic bandpass might fall off. There's a lot more work to do with this, but we should definitely chat more.
Great, thank you.
Great. Any other questions? All right, you can use my mic.
So thank you for a great talk. So I was wondering if you are including the covariance matrix in your retrieval, do you need to know the length scale and the amplitude of the correlated noise you have, or is there a way to basically include that you fit for that or retrieve that length scale as well?
That's a great question too. Here I'm assuming we know the amplitude and length scale, but there's been extensive work fitting for these parameters as well with retrievals for ground-based data. I think I highlighted a few papers at the beginning. I don't know if I should go back there. But yeah, this is also something people are doing for transmission spectroscopy right now. People fit for the Gaussian process hyperparameters. Sometimes they can retrieve them, sometimes they can't, but still an active problem that people are working on.
Thanks. And I have a quick question at the end, which is if you put error bars on that plot on the lower right, would the error bars actually look appropriately larger for the red points, or would it look like you had the correct answer with one realization of the just using the uncorrelated approximation?
Good question. They would look appropriately larger because I'm including the matrix. If you don't include the matrix, they look artificially too small.
Great, thanks. Let's thank Nicole again. Our second to last speaker is Megan DeLuca from the University of Washington and the NASA Virtual Planetary Lab.
Can you hear me now? Okay. So as Courtney said, my name is Megan DeLuca. I'm a PhD candidate at the University of Washington and graduating in the spring, so I'm on the job market. Please text your friends that left the conference and let them know. And I'm going to be telling you about a project that we did in collaboration with both industry and academia. I did this with Dr. John Ehrenberg at Northrop Grumman and Dr. Chris Stark at NASA Goddard. And we were looking at assessing the impact of stray light caused by micrometeoroid damage to the primary mirror. So to put this in context, micrometeoroid damage is unavoidable for space-based missions. You can do a lot to lower the probability or try and avoid really high energy impacts, but you're never going to get rid of it completely. And to that point, it's been consistent with pre-launch expectations, but JWST has seen a rate of a couple micrometeoroid impacts per month. For the most part, this has been totally fine, contributing less than a nanometer to the total wavefront error, with the exception of one, what I like to call low probability, high energy impact event in May of 2022. I'm sure you heard of this impact that happened on the C3 mirror segment. It was estimated to have an impact energy of around 7 to 26 joules. And so having such a high energy impact happen early in the mission really triggered a micrometeoroid working group, which eventually established the micrometeoroid avoidance zone for JWST. So I like this example because it's something that we should be aware of as we put more sensitive instruments into space, such as HWO. And for JWST and lots of space-based missions that have come before it, wavefront error is closely monitored in this context, but stray light caused by micrometeoroid damage is rarely concerning, and there's good reason for that. But for HWO, this is not necessarily going to be the case for a range of reasons, but in particular because HWO is concerned with characterizing such faint objects. Any stray light in your observation is it's going to be highly sensitive to that. So in this work, we were looking at order of magnitude estimates of stray light for an array of single hit impact energies. So we're only thinking about those low probability, high energy impacts, not the cumulative buildup of small impacts over time at this moment. So these are connected to expected reductions in exo-Earth candidate yields, which I'll talk about in a few slides. One other thing I want to point out is you'll see these two models come up, Watts and MR. These are the models that relate damage crater size to impact energy, and they end up having a pretty big effect on the results. And so in general, the Watts model predicts smaller craters, which is more optimistic for us, and the MR model predicts larger craters, which is more pessimistic for our reasons. I'm not going to spend too long here. I just like this visualization because it gives you a sense of what the model is doing. It's generating a 3D telescope model, which can have pretty much any barrel dimensions you want, as well as barrel rotation. And then it's looking at that telescope pointed on the sky. So for the background sources at the bottom here, we're using compiled Gaia data. So moving on to results, a telescope barrel in the context of micrometeoroid stray light can help you in two different ways. The first is that it can block incident stray light from background sources once there's already damage on your mirror. And the second way is that it can reduce that damage from ever getting there in the first place. So thinking about that first possibility for a minute, we looked at essentially how much stray light you're getting for different targets when you include all of the background sources in the sky versus just the host star only. So what you're seeing here is stray light versus impact energy or impactor mass. The left column is 3 targets from the HPIT catalog with the lowest galactic latitudes, and the right is the highest galactic latitudes. And then we're also seeing the difference between the Watts and MR model. And so overall, for impacts greater than 2 millijoules, these dashed lines and the solid lines are converging, which is telling you that the increase in stray light you're getting from considering the full sky background compared to just the host star only is negligible. And since the host star is going to be in your observation no matter what your barrel dimensions look like, that means that you're not getting a huge improvement from having a barrel in this case. I want to be very clear that this is just for the low probability, high energy impactors. I do not know if a barrel would help you out for the cumulative buildup of low probability or high probability, low energy impactors over time. If you want the answer to that, or any other question in the universe, you can pay me. This is just a reminder that I'm on the job market. Okay, now, the barrel does help you with the second reason, which is to reduce micrometeoroid impact damage in the first place. So you'll see that the stray light is going up orders of magnitude in cases for larger impactors. And so you really want to be preventing those super high energy impactors from coming about. So moving on to the yield results, we were using AYO, which was explained in great detail by Chris Stark on the first day. And essentially what we did was take 2 scenarios from his 2024 paper, which represent 2 designs. And we took their baseline yield that was calculated without any stray light, and then we imagined there was a single hit impactor on the mirror. And then we reran yield, assuming that that damage could contribute stray light for all sources. And what you're seeing on this plot is the % reduction from the baseline yield that you get in each case. So the first thing to notice is that there is a very big spread between the optimistic and pessimistic models, ranging from this is not ever going to be a problem to your mission is over. So that's something to be aware of. In general, impactors only start affecting yield if they're greater than 0.2 joules. And then in order to get a sense of what is actually going to be an impactor we should be worried about, 2 of my colleagues, John Ehrenberg and Blake Shepard over at Northrop Grumman, took 3 barrel designs inspired by the EAC designs and looked at what the maximum 2 sigma probability impactor would be over 5 years. So this is that impactor if you're pointed in the anti-ram direction, the favorable direction. And in general, for the pessimistic model, you're seeing reductions around 50% in yield, which is not fantastic. If you look at the difference between the shortest barrel and the longer barrel sizes, you get an additional 6% loss for the shortest barrel, again in that pessimistic case. Now, if you point in the ram direction, which is not so good, it gets a little bit worse. You go up to around 60% yield reduction total, with a difference of 9% between the best and worst barrel dimensions. So I wanted to try and anchor this in reality because the relationship between impact damage size and your loss in yield is so closely, is having such a great effect. And so our colleague Joe Pittman over at Heliospace was kind enough to let me know that they did an 8-joule impact test on a ULE, and it was found to produce a damage diameter of about 14 millimeters. So just to remind you, the C3 impact for GWST was around 7 to 26 joules. So I wanted to get a sense of what damage might be on the higher end of that energy. And unfortunately, the impact test closely, more closely matched the MR model than it did to the watts. So I did something super simple. I just used a polynomial fit to infer where a damage point might be on the higher end of that range. And it was found to be close to 30 millimeters. And now if you were to go back to those yield curves, I've done this all for you so you don't have to, and you were to infer the yield loss you would get, it would be between 2 to 4% up to 20 to 30% loss in yield for an 8 or 26 joule impactor, respectively. So this is, I think, really important. It's something we need to consider if we need to be prepared to either mitigate this possibility if we want to budget for a potential 20% loss in yield, or if there's things that we can do after an impact happens to get rid of it. Ask me about my ideas. The engineers hate them. Okay, so I'm going to leave you off with some parting thoughts. Number one, the benefits of a larger telescope barrel for this purpose specifically mainly come from a reduction in high energy impacts. Second, depending on the relationship between impact energy and damage diameter, the largest single hit impactors may reduce yield either negligibly or up to 50%, which is, in my opinion, too large of an error for us to have. And so to me, that means we need more impact testing, and we need to be really sure about this relationship when it comes to materials relevant for HWO. And lastly, we must understand the likelihood distribution of low probability, high energy impactors, and we have to budget for expected reductions in yield. So I don't want to see a mission going up that is expected to have a yield of 25, because any reduction is going to bring us below what we want to get. Thank you.
Questions? All right, to kick things off, you mentioned the engineers hate your ideas. Can you give us an example of one of your ideas?
I would love to. So nobody's taking me seriously, but I think we should do shark tooth mirrors. So you get mirror segments that are stacked, and when one gets damaged, you just blow it off, and then the next one comes.
What's the mass margin needed for that?
Don't worry about it.
Okay. Okay. All right. Well, in that case, I won't worry about it. Can you tell us about the physical difference between the two models for the impactors, the pessimistic and the optimistic cases? And then Renu has a question after me.
Yeah. So I would say the part about those two physical models, those really are coming from my colleagues over at Northrop. But what I would say is that they're very simple models. If you look at them plotted, they practically look like linear lines in a lot of cases. So that's like part of this work that scares me the most, I think, is that we don't have a really better idea of what that relationship should be at this point.
Thanks. Renu?
So do you assume a single layer of material in that barrel, or like there's multiple layers that the micrometeor has to like penetrate through, things like that?
Yeah, it's a good question. In this work, we were really focused on doing something kind of simple, first order. And so the barrel is, in this case, impenetrable. So you cannot get through the barrel if you hit it and you're a meteor. And there's also no bouncing.
Noah has a question in the corner. I guess that's not really a corner, sorry.
Noah Tushon Goddard. So my question was also about impacts to the barrel itself and stuff. I mean, I guess we probably haven't thought about this in this study, but it's interesting to consider potential like leaked sunlight if you have a hole in your barrel, like that would potentially affect your field of regard and like how close you can point to the sun, because otherwise you'd have like reflected sunlight coming into like a hole that was made into like the barrel, and like a lot of like instant light in your telescope that you wouldn't want. So yeah, that would be an interesting follow-up study.
Yeah. Yeah, I agree. I think that would be a fantastic study to do. I'd love to do it.
All right, any other questions? Okay, let's give Megan a round of applause. Okay, our final speaker of the session, so give yourselves a round of applause for being here till the end. You did it. Our final speaker is Akash Gupta from Princeton University.
Thank you. I'm perhaps the most hated person in this room right now. But again, thank you so much for sticking around till the very end. So, I'm a 51 Peggy CB fellow at Princeton University. And today I would like to share with you some new insights on the interaction of planet atmospheres and interiors, with a particular focus on those that are dominated by hydrogen and water. Now, this work is in collaboration with a number of people, but in particular, I believe focusing on the work with Lars Strickstrud and Hilka Schlichting. So, now a typical Earth to Neptune-sized planet accretes a primordial hydrogen atmosphere. We know this from a number of sources. One is exoplanet demographics, the theoretical and observational studies that have come up in this regard. We know this from our own solar system, and we see hints of this in the protoplanetary disk observations also. So all of this is telling us is that the planet formation and evolution process basically entails this interaction of the hydrogen with the rest of the planet for millions to billions of years, or at least they are in contact all this while. But most of our models often assume that the planet's atmosphere and interior just do not talk. But is this something that we need to worry about? Well, there are already studies, and I think we have already heard a number of talks that show and demonstrate that these interactions are indeed important. For instance, what you expect in the atmosphere is very much dictated what happens between the atmosphere and the silicates and so on, whatever else might be in the planet. After all, the mass of the planet is actually dominated not by the hydrogen, but the rest of it. There are also studies which indicate that there can be that there can be an impact at the demographic level of these interactions, and at a very nutshell, impact on the thermal evolution and structure of the planet atmosphere and interior. We even have observational evidence or hints of it from observations in this regard. For instance, here's the spectra of TOI-270d from JWST, and the authors basically inferred that what this tells you is that the mean molecular weight of this atmosphere should be something like 5.5. And this cannot be a pure hydrogen atmosphere. There are studies which even indicate that Earth might have had a primordial hydrogen atmosphere, and the atmosphere that you see today and our crust and interior that we have on Earth today are very much influenced by the presence of this primordial hydrogen atmosphere and reducing conditions. And then we even have Juno measurements indicating that Jupiter has a dilute fuzzy core. So whatever your favorite planet might be, these interactions have far-reaching consequences and will be important in understanding like the observations from HWO and other upcoming facilities. But if you actually play with these kind of models ever, or if you talk to your friends who do this kind of work, you will very quickly realize how little we understand about how these interactions actually happen. And if you think about it, our models can only be as good as our fundamental understanding of how these basic building blocks of planets actually talk to each other. Now, laboratory experiments are pretty hard. Many of our friends, Kara and others, are doing like a lot of hard work in this regard. But at the relevant conditions, things can be pretty difficult to achieve at some times. But a way to get around this is to use methods from quantum mechanics. Specifically, I would like to share with you how we can use ab initio molecular dynamics, something that is used across the fields of science, engineering, medicine, from the discovery of new drugs to new medicines, to like new materials. But we can also use that to understand how hydrogen and water could be interacting. Not only are these two of the most important molecules, building blocks of planets, but they can help understand planets in our own solar system and in our search of water-rich exoplanets out there, and those that could harbor liquid water ocean beneath hydrogen atmospheres, and essentially help us validate theories of formation and evolution, because again, we have planets, sub-Neptune-like planets in our own solar system, which can act like as benchmarks. Now, the typical paradigm of these interiors of, or like atmospheres and interiors of Neptune or sub-Neptune-like planets looks something like this. A hydrogen-rich atmosphere sitting on top of like a water layer or like a liquid water ocean. Or it could be like this, like a hydrogen-dominant region transitioning gradually to like a water-dominant region. But what is the reality? People often just pick one or the other, really. The reality can be figured out by appealing to like, what happens at the atomic level between these molecules, and by the so-called coexistence or critical curves of these mixtures. So consider this plot with temperature on the y-axis and pressure on the x-axis. So the critical curve basically encapsulates the Gibbs free energy of the participating species, tells you that where is it on this parameter space that the two species are completely miscible into each other, or where they are only partially miscible into each other. So keep this in mind, and let us look at how the results, let us see how the results look like. So on the y-axis, again, temperature, pressure on the x-axis. Keep in mind, though, that in this case, pressure is actually in log scale, and so it actually traverses 5 orders of magnitude. Now, this is how the experimental data that we have today looks like. And this is where different studies suggest that the atmosphere to water ice boundary might look for our Uranus and Neptune. And you can see that we only explored 3% of this parameter space through the laboratory experiments. And so this is where we explored this PTE space. Now, I want to emphasize that while these quantum methods can make it these much more extreme conditions accessible, these are also fairly complex and extremely computationally expensive. For instance, each of the dots that you're seeing here corresponds to 10 years of CPU time. Nevertheless, this helps us in figuring out this critical curve, which again divides this parameter space into this gray region where hydrogen and water will be completely miscible, and the blue region where they will only be partially miscible. And first of all, you should notice that there is good agreement with past experimental data, which is really important for these kind of studies. And so with that, let us look at some planetary scale implications. First of all, let us simplify. There was a lot of going on in that plot. Again, this black dashed line is a critical curve dividing where hydrogen and water completely mix or not. And here, for context, are the TP profiles of Uranus and Neptune. Something you will notice is that this is strikingly close to the critical curve. And that tells us that mixing of hydrogen and water is likely important in Uranus and Neptune today, and also in such planets that are there in our galaxy. Now consider this like an adiabat of this young Uranus or like hot sub-Neptune. As you can see, this adiabat lies completely in the gray region. So you expect a hot planet like this to have a completely mixed atmosphere interior. And it gives us clues to the recent observations of high mean molecular weight atmospheres, for example, for HWO25, because at such conditions, you will expect hydrogen and water or perhaps other molecules to be completely mixed. Now, over time, this planet will cool, and eventually it will end up intersecting this critical curve down in the outer regions of the atmosphere or down at at low pressures. And that is when the clouds will start to emerge. As time goes by, it will have another intersection deeper down inside the planet, and when that happens, note that that is where most of the mass of the atmosphere is actually located. And when that happens, first of all, there will be phase separation deeper down, sort of a rainfall that will happen deep inside the planet. And this is an important point in the planet's history, because you have to cross this line for there to be like liquid water deep down in the planet. And so this helps us narrow down the parameter space for planets that could have liquid water ocean beneath hydrogen atmospheres. And TOI-270d, for instance, if indeed dominated by hydrogen and water, cannot have like liquid water ocean as it is just too hot. Furthermore, as things further progress, like the planet further cools down, more rainfall, the hydrogen atmosphere will become further and further rich in its hydrogen content. There will be a change in composition of the atmosphere. These atmospheres will become metal poor over time, or in another way, metal poor with installation. So again, just understanding at a basic level what happens between these most important planet building blocks, you get so many insights. Not just that, we also get insights into the fundamental nature of matter. For instance, when these molecules become molecular to atomic, which can have its own implications for an envelope or interior opacities, electrical conductivity, magnetic field generation, and a lot of other things. Now, hydrogen water is an important system, but it is just one of them, right? There are a lot of other molecules and species that we need to take into account on how they're interacting and the interplay of different species. For instance, as was mentioned previously, like ammonia, what happens with ammonia? Then what about rock, interactions with rock? And then hydrogen, helium, and redox reactions. What about all these kind of reactions? So there's a lot of work that needs to be done in this direction. But to summarize about what I've what I've shared with you today, I hope I've convinced you that interaction of planetary building blocks are really consequential to understanding of planets and atmospheres. And it will be critical for contextualizing all these observations that we get from HWO. Experiments are tough, but in complement, quantum mechanical simulations can help us. And then I also shared with you some new computational experimental results, which give us new insights into the formation and evolution of exoplanets such as water-rich worlds or high-seen planets, and give constraints on where to find them. In addition, they also give us insights into solar system planets like Uranus and Neptune and fundamental properties of materials and their mixtures. To end with, Habitable Worlds Observatory will undoubtedly bring a paradigm shift in understanding Earth-like planets. But let us ensure that our understanding of fundamental physics and chemistry of planet-building materials propel us forward and never hold us back. And so there is a need at the community level for more investment into experiments and computational studies so that we can get a better handle on this front. And that is it from me. Thank you so much.
Questions. All right, you go first.
Hi, nice talk. I'm Komal from ETH Zurich. Nice work, but I have a question to you. How do you plan to establish the link to the planetary formation pathways?
So that in some ways connect to, when these planets are forming, a lot of this hydrogen could be getting dissolved into the water that is there, or the ice layer that is there, or the silicates that are there. So that is one place where it comes into play. So how much could actually be sequestered, deemed out inside these planets? So you need to consider how much capacity these planets have. So this, in some ways, comes into play there. Plus, what this is also telling you is that very initially, you might not actually have two layers of in a planet. You might not have a solid surface of any sort. Rather, there will be this fuzzy, basically, regime. And so that, again, that gives you a new perspective on how these planets actually form and evolve over time. Because typically, we just think of that, hydrogen atmosphere sitting on top of some solid rock layer or water layer or something. But that is not really the case. So those are a couple of ways in which this is giving us new insights into what could be happening.
Thank you. Thanks.
Vincent van UCL. Really nice talk. I was looking forward to this all day, so not the most hated person in the room at all. And you mentioned my favorite planet, so it was great. Really nice. I like the pressure temperature plots, but I kind of want to ask, as a sort of simple observer, these are not the kind of properties we typically directly observe for exoplanets. So can you comment a little bit on how to think of what you're seeing, properties like period radius kind of plots, or stellar type or stellar age or things like that? Like what kind of trends might you sort of generally expect to see, or what how can we translate into observable exoplanet properties?
So one thing is that you do want to build models, like you want to use this knowledge and build models that encapsulate this physics and figure out what happens. And this is something that we are working on, building new models that encapsulate this and other physics and chemistry. But to put it like one example, as I was mentioning here, you will expect, for instance, some sort of a trend towards atmospheres being metal poor with increasing age. The older you are, you might expect, if you are just hydrogen water dominated, this is what you would expect. Similarly, with decreasing installation, the cooler you are, or like the hotter you are, the more likely you will be in the gray regime that you are seeing here. So those are a couple of ways in which this connects with stellar and planetary properties. And similarly, you can connect that same thing with the stellar type for a given orbital period, like different flux for a different stellar type at a particular orbital period. So in those ways, this can connect. But ultimately, yes, you need some more modeling and to look at this at a demographic level. And that is something I am at the moment working on with some of my collaborators.
Really cool. Thank you.
Excellent. Any other questions? All right, one more. This will be our last question.
Hello, this is Alex Mendorowitz from Space Telescope. Could you say a little bit about your quantum mechanical simulations? How exactly are you setting them up? Is it Hamiltonian Monte Carlo, something fancier? I don't know.
Oh, it's not Newtonian Monte Carlo. So we are using density functional theory molecular dynamics. So I guess I do not have a setup of this. But in some ways, we are trying to mimic what experimentalists do, ideally, we are trying to set up a virtual experiment. What we do is that, first, as I was saying, we use density functional theory. We use the PV-Sol exchange correlation functional for this. And we basically do is that we take a box, put hydrogen in that, and we equilibrate it at different conditions, the relevant temperature pressure condition. We do the same thing with water. And then we just put them together and just let it evolve as a system would in nature. And as it evolves, we figure out, okay, do we get two different two coexisting phases or not? So if we get two complete coexisting phases, that tells you that, oh, hydrogen water at this particular temperature pressure just do not interact. On the other hand, if they completely mix, that tells you that, oh, at this temperature pressure, they completely mix. But there can also be intermediate regimes, which I did not really go into those details, but which we also try to quantify what it could be. But if you would like to talk more about the exact details of our density function theory calculations, I'm happy to chat more after this.
Great, thank you. And with that, let's thank Akash and all of our speakers and poster presenters again. And I also want to thank our fantastic mic runner and virtual moderator, Kamal. We wouldn't have been able to do this without you, and our AV team. So thank you to them, and thank you to the organizers for the conference. I think this is the end of the meeting. So don't remember to look around your seat, grab all the things you came with, and enjoy seeing updates from HWO. Are there any announcements from conference organizers? In the back. Okay. Okay, remove your posters before you leave, please. And if you haven't already, you can always post your posters on Slack, and you can get more feedback there. Thank you all.
And yeah.